Hello there and welcome to Life Beyond Seen, a place where curiosity settles in quietly, science slows its pace a little, and complex ideas are explored in a way that feels calm rather than hurried. This space has always been about taking familiar things and looking at them from angles that do not usually get attention, not to overwhelm the mind but to let it wander comfortably while learning something new. Some people listen while winding down after a long day, others while commuting, reading, or simply resting, and whatever brought you here today, the intention stays the same. The goal is to explore something fascinating without urgency, without pressure, and without the sense that every moment must be packed with intensity. Today the focus turns toward a body of water most people know by name even if they have never seen it in person. The Great Lakes, vast freshwater seas resting quietly between the United States and Canada, often appear so permanent that imagining them absent feels almost unrealistic. They shape weather, transportation, ecosystems, economies, and even cultural identity across a large part of North America. Standing on the shore of Lake Superior or Lake Michigan gives an impression closer to an ocean than a lake, with horizons that stretch until water blends into sky. Their scale makes them feel stable, almost immovable, like mountains made of liquid rather than rock. Yet there is a curious thought experiment that occasionally surfaces in scientific conversations and late-night discussions alike. It involves imagining those immense lakes slowly disappearing, not through evaporation in a typical seasonal sense, but through a hypothetical draining event. No dramatic catastrophe needs to be assumed for this exercise. Think instead of a gradual uncovering, as though a massive plug somewhere far below the surface had been opened and water began leaving the basins quietly over time. The idea itself is not about predicting a real event, it simply offers a way to examine what lies beneath waters that most people only ever see from above. If that scenario sounds slightly unusual, that is exactly why it's worth exploring. Hidden landscapes tend to hold stories, and the Great Lakes are young in geological terms, but old enough to have witnessed ice ages, shifting climates, human settlement, industrial growth, and environmental change. Beneath those surfaces are contours carved by glaciers, sediments laid down by ancient rivers, wreckage from storms long forgotten, and biological traces from ecosystems that existed before the lakes reached their current form. Removing the water in imagination allows those layers to become visible, at least conceptually, and once they become visible they start to tell a story. Before going further, a small moment of orientation can help. Wherever you happen to be listening, whether it is early morning, late evening, or somewhere in between, the pace here stays gentle. There is no rush to absorb everything at once. The topic unfolds gradually, and even complex science can be taken in slowly. Many people find that kind of pacing helps ideas settle more naturally, especially when the subject involves enormous natural systems that operate on timescales far longer than daily routines. If this sort of exploration feels relaxing or quietly interesting, a simple like or subscription helps the channel continue reaching people who enjoy thoughtful, slower-paced science conversations. It is never presented as an obligation, only as an option for those who find value in this calm style of learning. Communities built around curiosity tend to grow best when they grow naturally, and each listener contributes simply by being present. So, with that gentle housekeeping out of the way, the attention can return to the lakes themselves. Taken together, the Great Lakes contain about 1/5 of the world's surface fresh water. That statistic alone often surprises people. Lake Superior, Lake Michigan, Lake Huron, Lake Erie, and Lake Ontario form a chain connected by rivers and straits, each lake slightly lower in elevation than the previous one, until water eventually flows out through the St. Lawrence River toward the Atlantic Ocean. The system acts almost like a staircase of freshwater basins, shaped primarily by the retreat of massive glaciers at the end of the last ice age roughly 10,000 years ago. Glaciers behave like slow-moving bulldozers made of ice. As they advance, they scrape rock, deepen valleys, and carry sediment long distances. When they retreat, they leave depressions that often fill with meltwater. The Great Lakes basins are classic examples of this process. The glaciers did not simply melt and vanish. They sculpted terrain on a continental scale. Imagining those lakes drained means imagining the exposure of glacial carving on a scale rarely visible outside polar regions today. One immediate revelation would be the sheer unevenness of the lake floors. Many people picture lakebeds as relatively flat, perhaps sandy or muddy with gentle slopes. In reality, sonar mapping already shows complex topography. There are ridges, deep troughs, steep escarpments, and broad plains of sediment. Lake Superior alone reaches depths over 400 meters in some places. Removing the water would reveal landscapes resembling a mix of canyons, rolling hills, and broad valleys rather than a simple basin. Another element becoming visible would be ancient river channels. Before the glaciers reshaped the region, earlier river systems drained across what is now the Great Lakes Basin. Some of those channels remain buried under sediment, others are partially visible in geological surveys. Without the water, those channels would appear as winding depressions cutting across the exposed floor, reminders that landscapes constantly reorganize themselves over geological time. Human history would also surface quite literally. The Great Lakes have been major transportation routes for centuries. Storms, navigation errors, mechanical failures, and wartime incidents have sent thousands of vessels to the bottom. Some are famous, like the Edmund Fitzgerald in Lake Superior. Many others are small cargo ships, fishing boats, or early wooden vessels from the 19th century. Cold freshwater preserves wrecks unusually well compared with saltwater oceans, so draining the lakes would expose what is effectively a vast maritime archive. Industrial history adds another layer. For over a century, cities along the lakes discharged waste from factories, mines, and urban development. Environmental regulations have improved conditions significantly, yet sediments still contain traces of heavy metals, chemical pollutants, and microplastics. Exposure of those sediments would not be visually dramatic in every location, but scientific interest would be immediate. Researchers would study contamination patterns, ecological recovery processes, and historical industrial impact with unprecedented clarity. Biological consequences would be equally significant. Aquatic ecosystems in the Great Lakes support fish populations, bird migration routes, wetlands, and complex food webs. Removing the water in a hypothetical scenario would transform those ecosystems completely. Some species would migrate if possible, others would vanish locally. Terrestrial ecosystems would eventually colonize exposed land, but that transition would take time, influenced by soil composition, climate, and human activity. Observing such a transformation would provide insight into how ecosystems respond to rapid environmental change. Weather patterns deserve attention as well. Large bodies of water, moderate temperature. The Great Lakes store heat during warmer months and release it slowly during colder ones. This effect reduces temperature extremes in nearby regions and generates phenomena like lake effect snow. Without the lakes, winters in surrounding areas would likely become colder and summers hotter. Local agriculture, urban planning, and infrastructure would all adjust gradually to those new conditions. Freshwater availability introduces another practical dimension. Millions of people rely on the Great Lakes for drinking water, agriculture, industry, and transportation. Draining them, even hypothetically, emphasizes how dependent modern societies are on stable freshwater sources. It highlights infrastructure complexity, water management strategies, and the balance between natural systems and human needs. At a psychological level, landscapes shape identity. Cities like Chicago, Toronto, Cleveland, Milwaukee, and Buffalo grew around these lakes. Their waterfronts defined skylines, recreation habits, cultural traditions, and economic structures. Removing the lakes conceptually also removes familiar visual anchors. That sort of change often triggers reflection on how environments influence emotional attachment to place. Scientific curiosity continues extending outward from there. Exposed sediments might preserve pollen records, microfossils, and climate indicators from thousands of years ago. These data help reconstruct past climates, vegetation patterns, and ecological transitions. Such information improves climate modelling, archaeological understanding, and conservation planning. And then there is the simple visual aspect. A drained Great Lakes basin would not resemble a desert exactly, nor a typical valley. It would likely look like an enormous series of interconnected plains and depressions with residual rivers still flowing through lowest points. Shorelines would extend outward dramatically, revealing terraces formed by earlier water levels. Satellite imagery would show a fundamentally altered map of North America. Thinking about that, altered map leads naturally toward the broader idea of how temporary even large natural features can be on geological timescales. Mountains rise and erode, seas advance and retreat, lakes appear and vanish as climates shift. Human lifetimes are short compared with those processes, which sometimes makes current landscapes feel permanent even when they are not. The conversation gradually moves from imagination toward observation. Mapping technologies, underwater robotics, sediment cores, and sonar surveys already provide glimpses beneath the Great Lakes. Scientists do not need to drain them to learn about their flaws. Still, imagining the full exposure helps organize those pieces into a coherent mental picture. That picture continues expanding once attention shifts to how those lakes formed in the first place, because understanding origin often clarifies what might be revealed underneath, and the story of glacial formation turns out to be far more dynamic than many initial descriptions suggest, involving advancing ice sheets, meltwater pulses, temporary proglacial lakes, and dramatic shifts in drainage patterns that set the stage for everything resting there today. When people talk about the Great Lakes in everyday conversation, they often describe them simply as lakes, which sounds straightforward until you actually stand at one of their shores. The horizon stretches so far that it behaves visually like an ocean. Waves form with surprising force during storms, weather systems build over them, ships large enough to cross seas navigate their waters. Yet despite those ocean-like traits, the water is fresh, drinkable after treatment, and part of a delicate inland system that influences an entire region's climate, economy, and ecology in ways that rarely attract attention unless something unusual happens. Taken together, the 5 Great Lakes hold roughly 20% of the world's surface freshwater supply. That number alone tends to shift perception. Freshwater scarcity is an ongoing global concern, and the idea that one connected system contains such a large fraction of accessible surface freshwater underscores how geographically uneven water distribution can be. Lake Superior alone contains more water than the other 4 combined. Its sheer volume, combined with its depth, contributes to its reputation as the most formidable of the lakes, known for sudden storms, cold temperatures, and a long maritime history shaped by both trade and tragedy. Lake Michigan is the only one located entirely within the United States, though hydrologically it's often considered part of Lake Huron because they connect through the Straits of Mackinac with almost identical surface elevations. To someone unfamiliar with regional geography, they may appear separate on a map, yet water flows between them so freely that scientists frequently refer to them collectively. This kind of connectivity illustrates how artificial some geographic labels can be. Natural systems tend to operate as gradients rather than neat divisions. Lake Huron itself includes Georgian Bay, a vast extension with its own complex shoreline and thousands of islands. These islands influence local ecosystems, fisheries, and navigation routes. From above, satellite imagery shows coastlines that appear intricately carved, the legacy of glacial retreat combined with ongoing erosion and sediment deposition. Even without draining any water, mapping already reveals underwater ridges, submerged escarpments, and deep basins shaped by ancient ice movement. Lake Erie differs noticeably from the others in depth. It is the shallowest, which means it warms more quickly during summer and freezes more readily during winter. Those characteristics influence fish populations, algae growth, and seasonal weather. The shallowness also contributes to occasional ecological challenges, including harmful algal blooms linked to nutrient runoff from agriculture and urban areas. These issues receive attention because Erie supplies drinking water to millions of people, and maintaining water quality remains a constant balancing act between economic activity and environmental stewardship. Lake Ontario sits at the downstream end of the system before water exits toward the Atlantic Ocean via the St. Lawrence River. It is deeper than Erie but smaller in surface area compared with the upper lakes. Its position makes it crucial for shipping, hydroelectric power generation, and regional climate moderation. Cities along its shores, including Toronto and Rochester, experience milder winters than inland areas, largely because of the lake's thermal buffering effect. Depth across the system varies significantly. Lake Superior reaches depths over 400 metres. Lake Michigan approaches similar, though slightly shallower depths. Huron contains deep basins as well, while Erie remains comparatively shallow, averaging around 19 metres. Ontario returns to greater depths again. These variations affect circulation patterns, temperature layering, and oxygen distribution within the water column. Scientists refer to thermal stratification, a process where warmer surface water sits above colder, denser, deep water during warmer months. Seasonal turnover events mix these layers, redistributing nutrients and oxygen essential for aquatic life. Scale extends beyond water volume. The shoreline length of the Great Lakes collectively exceeds that of the Atlantic coast of the United States. That statistic surprises many people, because coastlines are often associated with oceans rather than inland freshwater systems. Yet the irregular shorelines, bays, peninsulas and islands create extensive interface between land and water. Wetlands form along many stretches, providing habitat for birds, amphibians, fish nurseries, and plant species adapted to fluctuating water levels. These lakes also function as major transportation corridors. Bulk cargo ships carry iron ore, coal, grain, limestone, and manufactured goods between industrial centres. The St. Lawrence Seaway allows ocean-going vessels to access interior ports, effectively linking North America's industrial heartland to global trade routes. Navigation infrastructure includes locks, dredged channels, lighthouses, and port facilities that collectively represent one of the largest inland shipping systems in the world. Weather interaction with the lakes remains one of their quieter but powerful influences. Large water bodies absorb solar heat slowly and release it gradually. That moderates nearby temperatures, reducing extreme fluctuations compared with inland regions at similar latitudes. During autumn and early winter, relatively warm lake water interacts with cold air masses moving across the surface. Moisture picked up by these air masses condenses as snow when reaching land, producing lake-effect snowstorms known for their intensity and localized impact. Wind patterns over the lakes generate waves capable of reaching several meters in height during storms. Mariners treat them with respect comparable to ocean conditions. The combination of sudden weather shifts, cold water temperatures, and limited shelter in certain areas has contributed to numerous shipwrecks over the centuries. Cold freshwater slows biological decay, which is why many wrecks remain relatively intact compared with ocean counterparts. Even without draining the lakes, underwater exploration continues, uncovering vessels preserved almost as historical time capsules. Ecologically, the lakes support diverse species including lake trout, whitefish, perch, walleye, and various migratory birds. Invasive species have also played a significant role in recent decades. Zebra mussels and quagga mussels, introduced via ballast water from transoceanic ships, altered nutrient cycles, water clarity, and food webs. Sea lampreys, another invasive species, impacted fish populations until extensive management programs reduced their numbers. These ecological dynamics illustrate how interconnected global trade and local ecosystems can become. Urban development around the lakes reflects both opportunity and challenge. Cities rely on water supply, transportation access, and recreational appeal. Waterfront redevelopment projects often focus on balancing public access, environmental restoration, and economic growth. Industrial legacy sites sometimes require cleanup due to past pollution. Environmental regulations, binational agreements between Canada and the United States, and ongoing scientific monitoring aim to protect water quality while supporting economic activity. Recreation forms another dimension of the lake's presence in daily life. Beaches, boating, fishing, kayaking, and coastal trails draw millions of visitors each year. Seasonal tourism contributes significantly to local economies. Cultural traditions emerge around these activities, shaping regional identity in subtle ways. Festivals, maritime museums, coastal parks, and historical reenactments maintain connections between present communities and their maritime heritage. Scientific research continues steadily across disciplines. Limnologists study freshwater systems, climatologists examine weather interactions, geologists analyze sediment cores, and ecologists monitor biodiversity. Remote sensing satellites provide large-scale data, while autonomous underwater vehicles collect high-resolution measurements from depths difficult for human divers to reach. These combined methods create increasingly detailed understanding of how the lakes function as integrated systems. Hydrologically, water levels fluctuate naturally due to precipitation patterns, evaporation rates, and inflow from rivers. Long-term climate trends influence these variables. Concerns about water diversion occasionally arise, especially during drought periods elsewhere in North America. Legal frameworks currently restrict large-scale diversion, recognizing both ecological risks and geopolitical sensitivities surrounding freshwater resources. Quiet power might be the most accurate way to describe the Great Lakes' influence. They rarely dominate headlines unless storms, pollution incidents, or unusual water level changes occur. Yet their steady presence shapes regional agriculture, energy production, fisheries, shipping logistics, urban planning, and climate moderation. Many residents grow accustomed to that influence without actively thinking about it. Thinking back to the earlier thought experiment about draining them, understanding their current scale and function provides context. The magnitude of change required to remove such volumes of water highlights how significant their absence would be. Every shoreline community, shipping route, ecological niche, and climate pattern connected to the lakes would shift in response. Mapping their depths already hints at what lies below. Sonar surveys reveal submerged river valleys, glacial grooves, sediment fans, and structural features inherited from bedrock geology. These details suggest that if the water were absent, the exposed terrain would not resemble a simple flat basin. It would display complex relief shaped by both ancient geological forces and more recent sediment deposition. That understanding leads naturally toward considering the mechanics of the hypothetical draining scenario itself. Imagining how water might recede, what sequence of exposures would occur, and how quickly landscapes would change becomes the next logical step, especially since gradual uncovering would reveal shorelines, slopes, and geological features in stages rather than all at once, allowing observation of transitions that normally remain hidden beneath calm freshwater surfaces. Thinking about what it would actually mean for the Great Lakes to drain requires slowing down and separating imagination from reality first, because nothing in current geology suggests they are about to vanish. This is not a prediction, not a hidden risk scientists are quietly worrying about. It is simply a structured thought experiment, the kind researchers sometimes use to understand complex systems by temporarily removing one major variable. In this case, that variable is an enormous volume of fresh water sitting in glacially carved basins that have existed in roughly their present form for thousands of years. The simplest way to picture the scenario is not a sudden catastrophic disappearance, not water instantly gone overnight, but a gradual lowering of levels over years or decades. That slower pace makes it easier to visualize consequences. Shorelines would shift outward bit by bit. Harbours would become shallower. Islands would grow larger as surrounding water retreated. Eventually, entirely new stretches of land would appear where waves once moved. Water leaving the system would have to go somewhere. In a purely hypothetical model, imagine an expanded outflow through the St. Lawrence River, perhaps combined with a geological opening that allowed additional drainage toward lower terrain. Again, this is theoretical, not something engineers or geologists consider plausible today. The point is simply to allow mental exploration of what exposure of the lakebeds might reveal and how human and natural systems would respond during the process. One immediate effect would be shoreline transformation. Current coastal cities are built with stable water levels in mind, even though natural fluctuations occur. A steady drop would leave docks stranded far from water. Marinas would require constant relocation. Wetlands would migrate outward, following the receding edge. Some species dependent on shallow coastal waters would shift habitats if possible, while others might decline locally. Sediment exposure would follow. Lake bottoms are not uniform sandboxes. Some areas consist of fine silts, deposited slowly over millennia. Others include gravel, clay layers, or exposed bedrock ridges. As water receded, wind would begin interacting with those sediments, potentially creating dust issues similar to what has been observed in smaller drained lakes elsewhere in the world. This alone would trigger environmental monitoring, especially near population centres. The pace of drainage would determine ecological adaptation. A very slow reduction might allow some aquatic species to migrate downstream gradually. Fish populations could redistribute along remaining waterways. Bird migration routes would adjust over time. Rapid drainage, on the other hand, would produce ecological stress far more abruptly for the purpose of calm exploration. Imagining a slow, observable process allows clearer understanding without focusing on crisis imagery. Navigation infrastructure would face constant adjustment. Shipping channels dredged to specific depths would become unusable. Locks and canals connecting lakes would require redesign or abandonment depending on remaining water flow. Ports that once handled bulk cargo might transition to land-based logistics hubs if rail and road networks expanded to compensate. Economic geography would shift quietly but persistently as transportation routes adapted. Climate influence would begin changing even before the lakes fully disappeared. As surface area shrank, seasonal heat storage would decline. Winters near the former shorelines would likely grow colder without large water bodies moderating temperature. Summers might become warmer. Lake effect snow patterns would weaken or vanish entirely. Agricultural zones dependent on moderated microclimates would adapt crop choices accordingly. Hydrologically, groundwater systems would respond. Large lakes exert pressure on surrounding aquifers. Lowering water levels could alter groundwater flow, potentially affecting wells, springs, and soil moisture regimes. Some areas might experience increased groundwater availability temporarily as sediments adjusted. Others might see declines. Hydrogeologists would monitor such transitions closely. Human psychology often attaches stability to familiar landscapes. The Great Lakes are part of regional identity in ways not always consciously recognized. A gradual retreat would create a prolonged period of adjustment. Former beaches would become grassy plains. Coastal property definitions would shift. Cultural landmarks tied to waterfront views would acquire new contexts. None of this implies panic. Rather, it reflects how humans steadily reinterpret environment when it changes. Infrastructure planning would evolve in parallel. Water intake systems for cities would extend further outward, following the retreating waterline until eventually alternative sources became necessary. Desalination would not apply, because this is fresh water, but river diversions, reservoirs, or conservation strategies might expand. Technological adaptation usually follows environmental change with a mix of innovation and practicality. Scientific interest would intensify quickly once exposure began. Geologists would map newly visible strata. Archaeologists would survey potential human artifacts previously submerged. Paleoclimatologists would collect sediment cores revealing pollen records, volcanic ash traces, and microfossils that document thousands of years of environmental history. Research vessels might give way to land expeditions moving across terrain once navigated by boat. The visual transformation would be gradual enough that photography and satellite imagery would document each stage. Time-lapse sequences spanning years would show coastlines creeping outward. Rivers feeding the lakes would carve new channels across exposed sediments. Vegetation would colonize moist ground first, followed by more diverse plant communities as soil stabilized. Freshwater redistribution beyond the basin would also become a topic of study. Increased flow through downstream rivers could affect estuaries, coastal ocean salinity patterns, and marine ecosystems. Even hypothetical scenarios require considering connected systems, because water cycles do not respect political or conceptual boundaries. Air quality might briefly change during early exposure phases. Fine sediments drying under sun and wind could produce localized dust until vegetation established itself. Similar phenomena occur in regions where smaller lakes or reservoirs have receded. Environmental management strategies would likely focus on stabilizing sediments through controlled revegetation. Legal frameworks governing water rights, navigation, fisheries, and environmental protection would require revision. International agreements between Canada and the United States currently manage Great Lakes water usage carefully. A draining scenario, even gradual, would introduce legal complexities related to land ownership, mineral rights, and resource management on newly exposed terrain. Energy systems would adjust as well. Hydroelectric facilities relying on lake outflows would see operational changes. Some might become obsolete if water levels dropped sufficiently. Others could adapt to new flow regimes. Regional energy grids tend to diversify over time, so adjustments would likely occur incrementally rather than abruptly. Tourism patterns would evolve in interesting ways. Initially, curiosity about newly exposed landscapes might attract visitors. Over time, recreation could shift toward hiking, ecological observation, or historical exploration of former lakebeds. Human interest in transformed landscapes often leads to new forms of engagement rather than disappearance of tourism altogether. Fisheries, both commercial and recreational, would transition gradually. Remaining connected waterways might support different species distributions. Aquaculture could expand to compensate for declining natural catches. These adaptations mirror responses already seen in regions experiencing environmental shifts for other reasons. Urban planning near former shorelines would require careful consideration. Exposed land might appear attractive for development, yet underlying sediments could remain unstable for years. Engineers would evaluate soil compaction, drainage, and long-term erosion risks before approving construction. Such caution typically follows any major environmental transformation. Educational institutions would treat the scenario as a living laboratory. Universities, environmental agencies, and international research collaborations would study ecological succession, sediment stabilization, climate feedbacks, and human adaptation. The opportunity to observe large-scale environmental change in real time would be scientifically significant. Public communication would play a steady role. Clear explanations help prevent misinformation when landscapes change. Scientists and policymakers generally emphasize transparency during environmental transitions, especially when they affect daily life indirectly through weather, economy, or water supply. Looking at the hypothetical draining in this measured way shifts focus away from dramatic imagery toward process. Large natural systems rarely change instantly. They evolve through sequences of adjustments. Understanding those sequences often provides more insight than imagining sudden disappearance. Once water levels dropped enough to expose deeper contours, the first fully revealed terrain would include sloping basin edges, terraces marking former water levels, and river deltas extending farther outward than currently visible. These transitional zones would offer early clues about what lies deeper beneath, setting the stage for examining newly exposed shorelines in more detail, especially since those initial exposures would likely attract both scientific teams and quiet observers curious about landscapes rarely imagined without water covering them. As the imagined waterline continued its slow retreat, the earliest visible transformation would not occur in the deep central basins most people picture when they think about the Great Lakes. It would begin quietly along the margins, where shallow coastal shelves currently extend outward beneath the surface. Those shelves already exist, mapped by sonar and underwater surveys, yet they remain mostly unseen except by researchers. With each incremental lowering of the lakes, these zones would emerge gradually, first as damp strips of sediment, then broader expanses of newly exposed shoreline that would look unfamiliar even to lifelong residents. The shift would not be dramatic at first. A few extra meters of beach, slightly longer walks from established docks to reach water, boat ramps extended, harbours dredged. The change might even seem temporary to casual observers, because natural fluctuations in lake levels already occur seasonally and across longer climate cycles. Only over years would the pattern become unmistakable. Coastlines once considered stable would inch outward steadily, revealing terraces that had been shaped during earlier lake stages thousands of years ago. These terraces are not theoretical. Geological studies have identified ancient shorelines around the Great Lakes Basin, dating back to post-glacial periods when meltwater levels fluctuated dramatically. Some of these former shorelines now sit well inland from current water levels. They appear as subtle ridges, gravel bars, or soil composition changes detectable through careful observation. As hypothetical drainage progressed, similar features would begin appearing closer to modern coasts, effectively adding a new chapter to an already complex shoreline history. Sediment composition would vary widely from place to place. Some regions would reveal sandy expanses similar to present beaches, while others would expose fine silts deposited slowly over centuries. Clay-rich zones might appear darker and retain moisture longer, forming temporary wetlands before stabilizing. In rocky areas, especially along parts of Lake Superior and Georgian Bay, exposed bedrock would dominate. These differences would influence how quickly vegetation established itself and how easily humans could traverse the new terrain. The slope of the basins would become increasingly apparent as exposure progressed. Contrary to a common mental picture of lakebeds as flat bowls, many areas descend gradually for long distances before reaching deeper troughs. Walking across those slopes would feel similar to traversing very broad, gently inclined valleys. In some places, however, escarpments would appear where underlying bedrock rises sharply. These structural features already shape underwater circulation patterns, and their exposure would provide a clearer visual understanding of how geology influences lake behaviour. River deltas would also extend outward visibly. Rivers feeding the lakes carry sediment that settles where flow velocity drops. Over time, this creates fan-shaped deposits at river mouths. Currently, much of that sediment lies underwater, but as levels declined, deltas would advance across newly exposed ground. Channels would adjust accordingly, sometimes meandering unpredictably as they sought the lowest path toward the receding water. Wetlands would migrate as well. Coastal marshes depend on specific water depths and seasonal flooding patterns. As the shoreline moved, plant communities adapted to saturated soils would follow. Cattails, reeds, sedges and other wetland species would colonize freshly exposed mudflats relatively quickly. These zones often become important habitats for migratory birds and amphibians, so wildlife patterns would shift gradually, rather than disappear outright. Human infrastructure along the coasts would experience subtle but persistent pressure to adapt. Municipal water intakes would extend farther outward through pipelines. Harbours would either expand seaward or, if adaptation proved impractical, gradually lose relevance. Beachfront property definitions would change legally and practically, sometimes creating disputes about ownership of newly exposed land. Historical precedents exist in smaller-scale shoreline shifts, offering legal frameworks but not always easy solutions. The visual character of the lakes would transform slowly enough that photography would capture an evolving mosaic rather than a sudden before and after contrast. Aerial images would show expanding bands of lighter-coloured sediment bordering darker open water. Over time, those bands would widen into plains. Satellite monitoring already tracks shoreline changes caused by seasonal variations. In this imagined scenario, similar tools would document long-term retreat. One interesting aspect of newly exposed shorelines involves smell, something rarely considered in large-scale environmental discussions. Freshly uncovered sediments can release organic odours as previously submerged plant material interacts with air. These smells usually fade as drying progresses and microbial communities stabilise. Observations from smaller receding lakes suggest that initial odour changes are temporary but noticeable. Wind patterns would begin interacting with exposed terrain differently than with open water. Water surfaces absorb wind energy differently than land. As more sediment became exposed, local microclimates near the former shoreline would adjust. Breezes that once travelled across uninterrupted water might weaken slightly or change direction due to new landforms interrupting airflow. Meteorologists would track these subtle shifts carefully. Seasonal ice formation, currently common on the shallower lakes, would diminish as surface area decreased. Ice cover influences winter albedo, evaporation rates, and heat exchange with the atmosphere. Reduced ice formation would feed back into regional climate patterns, though gradually rather than abruptly. Such feedback loops are complex and typically studied over long time scales. Public perception would likely evolve in stages. Initial curiosity might dominate, with people visiting expanded beaches or photographing unusual coastal views. As changes continued, normalization would occur. Humans adapt visually to environmental change more quickly than often expected. Landscapes that once seemed unusual become familiar surprisingly fast. Transportation adjustments would extend beyond shipping. Coastal highways built near current shorelines might find themselves farther inland relative to water. Some communities might consider new waterfront development opportunities, while others might prioritize conservation of emerging wetlands. Urban planning decisions would reflect local priorities as much as environmental constraints. Scientific teams would take advantage of early exposures before deeper basins became accessible. Shallow zones often preserve valuable sediment records. Core samples extracted from these areas can reveal pollen history, volcanic ash deposits, microplastic accumulation trends, and other environmental indicators spanning centuries or millennia. Researchers typically collect such cores from boats today. Land access would simplify certain aspects while introducing new logistical considerations. Biological colonization of exposed shorelines tends to follow predictable succession patterns. Pioneer plant species tolerant of fluctuating moisture establish first. Their root systems stabilize sediments, reducing erosion. Gradually, more complex plant communities develop. This ecological progression could be observed directly across vast areas, offering insight into landscape recovery processes relevant far beyond the Great Lakes region. Noise levels near former shorelines would change subtly. Water surfaces absorb sound differently than land. As open water receded, acoustic environments would shift. Waves breaking on distant beaches would no longer dominate the background soundscape in certain areas. Instead, wind moving across grasses or newly forming vegetation might become more noticeable. Such sensory details rarely appear in large-scale environmental analyses, yet they shape everyday experience. Recreational activities would evolve accordingly. Boating distances from existing marinas would increase, encouraging relocation or redesign of facilities. Beachcombing, birdwatching, hiking, and geological exploration might gain popularity in newly accessible areas. Cultural adaptation often follows environmental change through shifts in recreation and tourism patterns. Underlying all these gradual adjustments is the recognition that basin slopes lead eventually toward deeper central regions. Early shoreline exposure would only hint at the more dramatic terrain still hidden farther out. Geological surveys already show submerged ridges, ancient channels, and structural features that would become clearer only after significant water loss. Observing the first exposed margins would therefore act as a prelude to deeper revelations. This naturally brings attention toward those deeper landscapes themselves. Once the initial shorelines and gentle slopes became familiar features rather than novelties, curiosity would turn increasingly toward what lay farther out across the expanding basin floors, particularly the remnants of older river systems that existed long before glaciers sculpted the lakes into their present forms. As the imagined waterline continued its gradual retreat beyond the gently sloping margins, attention would begin shifting toward features that are already known to exist but remain hidden beneath hundreds of meters of fresh water. Long before glaciers carved the Great Lakes basins into their present shapes, this region was drained by entirely different river systems. Those ancient rivers followed courses determined by bedrock topography, tectonic stability, and climates that looked nothing like today's northern Midwest and southern Ontario. Draining the lakes in this thought experiment would eventually expose traces of those prehistoric landscapes, revealing a terrain far older than the water currently covering it. To understand what would appear, it helps to recall that glaciers do not create landscapes from nothing. They modify what already exists. When the last major ice sheets advanced across North America roughly 20,000 years ago, they scraped, deepened, and widened existing valleys. In some places they scoured down to bedrock. In others they deposited thick layers of sediment. Beneath the Great Lakes today lie remnants of valleys carved by rivers that once flowed across a temperate continent free of continental ice sheets. Geophysical surveys using seismic imaging and sonar have already identified buried channels beneath portions of the lakebeds. These channels appear as elongated depressions cut into bedrock, sometimes filled with glacial sediments. They represent former river valleys that predate the last ice age, and in some cases they may be millions of years old. If water levels dropped sufficiently in this hypothetical scenario, those buried systems would gradually emerge as visible depressions cutting across the exposed basin floors. The scale of these valleys would vary. Some would resemble modest riverbeds, shallow and winding. Others could appear as broad, deeply incised corridors several kilometers wide, depending on how much erosion occurred before glaciation. Walking across them would not feel like traversing small streams, but rather descending into large troughs shaped by long-extinct river systems. Their orientation might not align with present drainage patterns, which would add to the sense of standing on a landscape shaped by rules no longer active. Sediment layers would tell part of the story. Glaciers often filled older valleys with till, sand, gravel and clay as they advanced and retreated. When exposed, cross-sections along valley walls would display distinct strata. Coarser gravels might mark ancient river channels. Overlying clays could represent glacial deposition. Above that, fine lake sediments might document the post-glacial era. These layered records would provide an accessible visual timeline of environmental change spanning vast stretches of geological history. In some regions, ancient river valleys might connect to current river systems, offering insight into how drainage reorganized after the glaciers melted. When ice retreated, massive meltwater pulses created temporary proglacial lakes and redirected water along new routes. The modern configuration of the Great Lakes emerged from that chaotic period. Exposing older valleys would highlight how different the drainage network once was, demonstrating that what seems permanent in one era can be temporary in another. Bedrock composition beneath these valleys would influence their appearance. Portions of the Great Lakes Basin rest on sedimentary rock such as limestone, shale and sandstone. In other areas, especially around Lake Superior, ancient Precambrian crystalline rocks dominate. Valleys cut into softer sedimentary rock might appear broader and smoother, while those incised into harder crystalline formations could display steeper walls and more rugged features. Such contrasts would make geological boundaries visible in a way currently accessible only through specialized surveys. Vegetation would begin colonizing exposed valley floors relatively quickly if moisture remained available. Ancient channels often occupy slightly lower elevations, meaning groundwater might persist there longer than on surrounding slopes. Early plant communities would likely concentrate in these depressions, tracing the outlines of prehistoric rivers much like modern rivers support green corridors across drier landscapes. Archaeological implications would also emerge. While most human settlement in this region occurred after the last glacial retreat, there remains potential for early post-glacial sites near former shorelines of proglacial lakes. As drainage patterns shifted thousands of years ago, human groups followed water sources. Newly exposed valleys might contain artifacts or settlement traces from early inhabitants who occupied transitional landscapes during dynamic environmental change. Paleoclimatologists would find particular value in these ancient channels. Sediments trapped within buried valleys often preserve pollen grains, plant remains, and microfossils. Such materials reveal information about past vegetation, temperature, and precipitation patterns. Access to these records on land rather than beneath water would simplify sampling and expand the scale of analysis. Reconstructing pre-glacial ecosystems helps scientists understand long-term climate cycles beyond the relatively short instrumental record of modern meteorology. Hydrologically, some of these prehistoric valleys might still influence groundwater flow today. Even when filled with glacial deposits, buried channels can act as conduits for subsurface water movement. Exposure would allow direct mapping of their geometry, improving understanding of regional aquifer systems. Groundwater studies rarely capture public attention, yet they are critical for long-term water resource management. Standing within one of these exposed valleys would likely produce an unusual perspective. Surrounding slopes that once descended toward open water would instead frame a dry trough, leading toward deeper basins yet to be uncovered. The absence of waves and shifting reflections would make the underlying structure more apparent. Subtle curvature in valley walls, meander patterns frozen in bedrock, and sediment fans marking former tributaries would become easier to read visually. The scale of time involved in shaping these features stretches far beyond human experience. Rivers carving valleys operate over tens or hundreds of thousands of years. Glaciers modifying those valleys add another layer of long-duration processes. Draining the lakes hypothetically would compress the revelation of those long histories into a span observable within a human lifetime. That contrast between the slow pace of geological formation and the relatively rapid pace of exposure would likely shape public fascination. Comparisons with other regions provide context. In parts of Europe and Asia, ancient river valleys now lie submerged beneath modern seas due to rising sea levels after the last ice age. There, marine geologists use sonar and drilling to study landscapes similar in age to those beneath the Great Lakes. The difference in this thought experiment is scale of accessibility. Exposed freshwater basins would allow direct terrestrial exploration without deep-sea equipment. Wind and erosion would begin modifying valley walls once exposed. Sediments left unsupported by water might slump gradually. Vegetation would stabilize some slopes, while others might experience minor landslides. These processes would alter valley appearance slowly, meaning the earliest years after exposure would offer the clearest glimpse of their preserved form before weathering softened edges. The alignment of prehistoric valleys relative to current compass directions might reveal tectonic influences that are subtle but present in North America's interior. Although this region is tectonically stable compared with plate boundaries, ancient fractures and structural trends in bedrock influence river courses long before glaciation. Observing valley orientation directly could illuminate those structural controls. Educationally, such exposures would transform geology curricula across the region. Students currently learn about buried channels through diagrams and cross-sections. Being able to stand within one would provide a tangible understanding of erosional processes. Field studies would likely become more common, with researchers and students mapping features in detail. As exposure progressed deeper into the basins, some valleys might intersect with submerged ridges formed by glacial moraines. Moraines are accumulations of debris left at glacier margins. Where prehistoric rivers once cut through bedrock, later glaciers may have partially filled those channels with moraine deposits. Seeing these overlapping features would illustrate the layered complexity of landscape evolution. All of this would gradually build a clearer mental image of what the region looked like before massive ice sheets reshaped it. Forests would have lined riverbanks. Climate conditions would have differed. Drainage might have flowed southward or westward in patterns unfamiliar to modern observers. The Great Lakes themselves would not yet exist in recognizable form. Once these prehistoric river valleys became fully visible across large stretches of the basin floors, curiosity would naturally extend toward another layer of hidden history. Beyond rivers and glacial deposits lie stories preserved not only in rock and sediment, but also in objects left by more recent human activity, particularly the vessels that once crossed the surface above and now rest silently where water currently shields them from view. As the imagined retreat of the Great Lakes continued past ancient river valleys and expanding sediment plains, another layer of hidden history would gradually emerge, one tied not to glaciers or prehistoric climates, but to human movement, commerce, exploration, and sometimes simple misfortune. The Great Lakes have served as major transportation corridors for centuries. Long before highways and air freight dominated logistics, ships carried timber, grain, iron ore, coal, manufactured goods, and passengers across these inland seas. That long maritime history inevitably includes losses, storms, navigation errors, mechanical failures, fires, collisions, and winter ice all contributed to vessels sinking in waters that, until now in this thought experiment, have preserved them unusually well. Freshwater preservation is one of the defining characteristics here. Unlike saltwater oceans, which host wood-boring organisms such as shipworms, the cold freshwater of the Great Lakes slows biological decay dramatically. Low temperatures in deeper areas further reduce microbial activity. The result is that many shipwrecks remain intact for decades or even centuries, sometimes with paint, cargo, and structural detail surprisingly well preserved. Divers exploring known wreck sites today often describe them as suspended moments of history rather than deteriorating ruins. If the lakes drained gradually, the first shipwrecks revealed would likely be those already lying in relatively shallow water near historic shipping lanes and harbour approaches. These might include fishing boats, small cargo vessels, recreational craft, and early steamships lost close to shore. Their emergence would initially attract local attention rather than international headlines. Photographs would circulate, maritime historians would document conditions, and conservation discussions would begin immediately. As exposure extended farther into deeper basins, larger vessels would appear. Some of the most famous wrecks in Great Lakes history rest in deeper waters, including large freighters lost during sudden autumn storms. The story of the Edmund Fitzgerald, for example, remains widely known even among people far from the region. That ship sank in Lake Superior in 1975 during severe weather, taking all crew members with it. Cold deep water has preserved the wreck in remarkable condition. Seeing such vessels exposed would likely carry emotional weight beyond simple historical curiosity. Maritime archaeology would expand rapidly under these conditions. Currently, studying deep wrecks requires specialized equipment, remotely operated vehicles, or technical diving expeditions. Land access would simplify certain aspects while introducing new preservation challenges. Exposure to air accelerates deterioration for materials long submerged. Wood dries and cracks. Metals oxidize faster. Conservation teams would likely prioritize documentation and stabilization quickly after exposure. Cargo contents could provide insight into past economic patterns. Grain shipments, iron ore, machinery, timber, coal, automobiles, and manufactured goods have all travelled these waters. Some cargo might still be contained within holds, protected by hull structures. Historians use cargo manifests today, but direct observation of preserved cargo would add another layer of understanding to industrial and trade history. Navigation technology evolution would also become visible. Early wooden sailing vessels, transitional steamships, steel-hulled freighters, and modern cargo ships all share the lakes. Seeing representatives from different eras side by side across an exposed basin floor would illustrate technological progression clearly. Hull design changes, propulsion systems, safety equipment, and cargo handling methods reflect broader industrial development. Weather remains a central factor in many Great Lakes shipwreck stories. Sudden storms, especially during late autumn when temperature contrasts intensify, have historically produced large waves and powerful winds. Mariners sometimes refer to November gales as particularly dangerous. These storms form quickly and can overwhelm vessels not designed for extreme conditions. Wreck distributions often align with known storm tracks and shipping routes. Ice hazards historically contributed to losses as well. Before modern ice-breaking capabilities improved navigation safety, winter voyages carried significant risk. Ships trapped in ice could suffer hull damage or drift into hazards. Some wrecks occurred not from storms but from structural stress caused by freezing conditions. These vessels, if exposed, would represent another dimension of maritime adaptation to seasonal freshwater environments. Human stories attached to these wrecks vary widely. Some involve tragic loss of life, others ended with successful rescues despite ship loss. Maritime communities around the lakes maintain oral histories, memorials, and cultural traditions connected to these events. Exposure of wrecks might revive those stories publicly, linking modern observers with past communities dependent on lake transportation. Environmental considerations would accompany archaeological interest. Some wrecks contain fuel residues, industrial cargo, or hazardous materials. While long submersion often stabilizes such contents, exposure could require environmental assessment. Authorities would likely coordinate monitoring and remediation where necessary, balancing historical preservation with ecological safety. Tourism interest would grow steadily. Maritime museums, already present in several Great Lakes cities, might expand exhibitions. Guided tours of accessible wreck sites could develop where safety allowed. However, preservation concerns often limit unrestricted access. Experience from terrestrial archaeological sites suggests that controlled visitation helps protect fragile structures, while still supporting education. Legal frameworks governing wreck ownership would come into focus. Admiralty law, heritage protection statutes, and international agreements between Canada and the United States already address underwater cultural resources. Exposure would shift some legal interpretations because sites previously protected by depth would become land-based heritage locations. Policymakers would likely clarify jurisdiction, conservation standards, and research access. Technological documentation methods would evolve quickly. High-resolution scanning, photogrammetry, and digital modelling allow detailed recording of structures before deterioration progresses. These techniques are already used underwater. On land, they become easier to deploy across multiple sites simultaneously. Digital archives could preserve shipwreck details even if physical preservation proves challenging. Educational outreach would likely accompany these efforts. Schools, universities, and public media tend to highlight tangible historical discoveries. Shipwrecks combine engineering, economics, climate history, and human narrative in ways accessible to broad audiences. Interdisciplinary research opportunities would expand accordingly. Cultural perceptions of the lakes might shift subtly. Many residents currently think of them primarily as recreational spaces or economic resources. Visible wreck fields would reinforce their role as historical transportation corridors, emphasizing continuity between past and present regional identity. Biological colonization of exposed wrecks would begin gradually. Submerged ships often host aquatic ecosystems including algae, mussels, fish and invertebrates. Once exposed, those communities would decline or relocate. Terrestrial organisms would eventually colonize structures, especially if wood remains intact long enough to support plant growth. This ecological succession on artificial substrates offers another research avenue. Preservation contrasts between freshwater and saltwater wrecks would become easier for the public to understand visually. Ocean wrecks often deteriorate rapidly due to salinity, corrosion and marine organisms. Seeing well-preserved Great Lakes vessels firsthand would illustrate how environmental chemistry influences archaeological survival. Not all wrecks would be dramatic cargo ships. Smaller craft used for fishing, transport, exploration or recreation would appear as well. These vessels often receive less historical attention, yet reflect everyday economic activity. Documenting them provides a fuller picture of regional maritime life beyond headline-grabbing disasters. Over time, as exposure progressed into deeper zones, the distribution of wrecks might reveal patterns tied to historical shipping lanes. Mariners generally follow efficient routes shaped by geography, weather patterns, and navigational hazards. Mapping wreck locations could therefore reconstruct historical traffic corridors even where written records are incomplete. Some wrecks may have never been located precisely while submerged. Their sudden appearance on land would resolve long-standing maritime mysteries. Families of lost sailors, historical societies, and researchers often maintain interest in such cases across generations. Closure in historical terms does not erase tragedy, but can complete narratives left unfinished. Economic implications extend quietly into heritage industries. Conservation, tourism, research funding, museum expansion, and educational programming all create employment opportunities. Regions with strong maritime identity might incorporate exposed wrecks into broader cultural development strategies. As the lakebeds revealed more of these preserved vessels, the layered relationship between geology, climate, and human activity would become increasingly evident. Ships sank partly because of weather influenced by large freshwater bodies shaped by glacial history. Exposure of wrecks alongside ancient river valleys and sediment terraces would visually connect natural processes with human enterprise. That layered connection naturally leads toward another geological dimension still partially hidden, even in current surveys. Beneath shipwrecks, sediments, and ancient channels lie structural features carved by ice itself, ridges, grooves, and fault-related formations that shaped the basins long before any vessel crossed their surfaces, and those geological scars would become clearer as deeper sections continued emerging from beneath the retreating freshwater. As more of the basin floors emerged in this gradual thought experiment, attention would begin shifting from human artifacts resting on the surface to the deeper structural framework that shaped the lakes long before any ship crossed them. Beneath sediments, beneath wrecks, beneath even the prehistoric river valleys, lies the geological architecture that determined where water could collect in the first place. Draining the Great Lakes would not create that structure. It would simply reveal it more clearly. The Great Lakes region sits on ancient continental crust. Much of the surrounding bedrock, especially near Lake Superior, belongs to the Canadian Shield, composed of some of the oldest rocks on Earth. These rocks formed billions of years ago and have endured cycles of mountain building, erosion and tectonic stability. While the region today is not tectonically active in the dramatic way that plate boundaries are, its ancient fractures and structural trends still influence topography. Fault lines in this region are generally old and relatively inactive. They do not produce frequent large earthquakes, yet they remain part of the crust's structural history. Some lake basins align with zones of crustal weakness that predate glaciation by hundreds of millions of years. If water receded fully, certain linear depressions might trace those ancient fault systems. Their presence would not indicate new instability, but rather expose the deep time story of continental assembly and separation. Lake Superior, in particular, sits within a geological feature known as the Mid-Continent Rift, a massive failed rift system that began forming about 1.1 billion years ago. At that time, the continent attempted to split apart. Magma rose, volcanic rocks formed, and the crust stretched. Eventually the rifting stopped before fully separating the landmass, leaving behind thick volcanic deposits and structural troughs. Today the lake occupies part of that ancient rift valley. Draining it would expose large expanses of basalt and other volcanic rocks, shaped by both tectonic forces and glacial erosion. These volcanic formations are already visible along certain shorelines, especially in northern Minnesota and Ontario, where dark cliffs and ridges reflect the rift's history. Beneath the lake surface, similar formations continue across the basin floor. Once exposed, they would appear as ridged landscapes of solidified lava flows, layered in sequences that geologists use to interpret the rift's evolution. Seeing such formations uninterrupted across wide areas would provide a striking visual reminder that this region's geological story extends far beyond the recent ice ages. Glacial carving overlays that tectonic foundation. During the last glacial maximum, ice sheets thousands of meters thick advance repeatedly across the basin. Ice acts not only as a scraper, but also as a polisher and excavator. It grinds rock beneath it, plucks blocks from bedrock, and transports debris long distances. As glaciers move, they leave behind distinctive marks such as striations, grooves, and roche-moutonné formations, asymmetrical rock hills smoothed on one side and steep on the other. Currently, many of these glacial features are visible along exposed bedrock shores. With drainage, they would extend across entire basin floors. Long parallel grooves etched into bedrock would indicate ice flow direction. These grooves can be meters long and aligned consistently across large areas. Their orientation reveals the movement patterns of ancient ice sheets more clearly than many maps alone. Moraines would also become prominent. These ridges of glacial debris mark positions where ice paused or stabilized during retreat. Some moraines already form visible hills inland from current shores, but others lie submerged beneath lake waters. Exposed, they would appear as elongated ridges composed of mixed rock fragments, sand and clay. Walking along one would feel like traversing a natural embankment built from material carried hundreds of kilometers by ice. Drumlins, streamlined hills formed beneath moving glaciers, might appear in certain areas. These features align with ice flow direction and consist of compacted sediment shaped into smooth elongated mounds. In regions where glacial sediments are thick, drumlin fields can cover large expanses. If present beneath the lakes, their emergence would illustrate the power of moving ice in reshaping entire landscapes. Bedrock ridges beneath the lake sometimes form submerged escarpments that currently influence water circulation. Without water, these ridges would stand as elevated spines across the basin floors. Some might be steep enough to create localized cliffs. Others would form broad uplands dividing deeper depressions. Such relief would challenge the idea that lakebeds are uniformly flat. Fault-related structures could also interact with glacial features. Ancient fractures sometimes guide erosion, because fractured rock weathers more easily. Glaciers moving across these weakened zones may have deepened them preferentially, contributing to basin formation. Exposed intersections of faults and glacial grooves would highlight how multiple geological processes layered upon one another over immense timescales. Sedimentary rock layers in parts of the basin would reveal fossil content when exposed. Limestone and shale formations often contain marine fossils from periods when this region lay beneath shallow seas hundreds of millions of years ago. Draining the lakes would not create new fossils, but broader exposure would increase accessible outcrops for study. Paleontologists might examine large continuous surfaces that are currently mapped indirectly. The interplay between tectonic stability and glacial excavation explains why the Great Lakes occupy their specific positions. The crust provided structural lows and zones of weakness. Glaciers deepened those lows and scoured out softer material. Meltwater filled the depressions after ice retreat. Observing the raw bedrock beneath would connect these stages clearly. Wind erosion would begin modifying exposed bedrock slowly but noticeably in some areas. Fine sediments blown across surfaces can abrade rock gradually. However, bedrock itself weathers over much longer timescales than loose sediment, meaning many glacial carvings would remain visible for decades or longer before significant alteration occurred. In some deeper zones, isostatic rebound effects might become more apparent. When massive ice sheets melted, the crust began rising slowly after being compressed under their weight. That process continues today in parts of the region. Exposing the basin floor might allow direct observation of subtle tilting or differential uplift patterns that have influenced shoreline changes since the last glaciation. Groundwater seeps could emerge along fault lines or fractures once water pressure from above decreased. Springs often follow structural weaknesses in rock. With lake levels gone, some previously submerged seeps might become visible trickles emerging from bedrock faces. Hydrogeologists would study such features to better understand subsurface water pathways. The colour palette of the exposed geology would vary significantly. Dark basalt from the mid-continent rift contrasts with lighter sedimentary rocks. Iron-rich formations might show reddish tones. Clay deposits would appear grey or brown. Such contrast would create a mosaic across the basin floor, visible even from aerial perspectives. Over time, vegetation would colonize stable rocky surfaces where soil accumulated in cracks. Lichens often pioneer exposed rock, gradually contributing organic material that allows mosses and eventually higher plants to establish. This slow ecological succession would overlay the geological framework with a developing biological layer. Public interest in exposed geological scars would likely focus first on dramatic cliffs or ridges, yet subtle features such as glacial striations may hold greater scientific value. Researchers would document orientations carefully, comparing them with existing regional maps to refine models of ice sheet movement during the last glacial cycles. The presence of structural troughs and ridges beneath the lakes also explains current depth variations. Lake Superior's deepest sections align partly with rift-related depressions. Understanding that context becomes easier when standing directly within those depressions rather than viewing them through sonar data alone. As these geological scars came fully into view, the region's history would appear layered. Ancient tectonic rifting, marine sediment deposition, long periods of erosion, massive glacial sculpting, meltwater reorganization, and finally human navigation across freshwater surfaces. Each layer remains physically present, stacked in time though now exposed in space. Seeing these foundations clearly would shift perspective away from the water itself toward the deeper forces that created the basins. And once those tectonic and glacial features became familiar landmarks on the exposed floor, curiosity would naturally move backward even further toward the climatic era that transformed this structural framework into the lakes known today, the immense ice age that reshaped North America and set the stage for everything resting here now. The geological scars already imagined across the exposed basin floors start making more sense once attention shifts toward the period that shaped them most dramatically, the long sequence of ice ages that transformed northern North America. The Great Lakes did not appear suddenly. They developed through repeated advances and retreats of continental glaciers, each cycle modifying the land a little more until the basins deepened enough to hold the vast freshwater system now familiar. Removing the water in this thought experiment would therefore uncover not just rock and sediment, but the physical record of how ice itself behaved over thousands of years. Around 2 million years ago, Earth entered a climatic phase marked by recurring glacial periods. These cycles were driven largely by variations in Earth's orbit, axial tilt, and solar radiation distribution. Temperatures cooled enough for snow accumulation to exceed melting in high latitudes. Over centuries, compacted snow transformed into ice sheets that spread outward. The Laurentide ice sheet, the one most relevant here, eventually covered much of Canada and extended deep into what is now the northern United States. Ice sheets are not static blankets. They move slowly under their own weight, sometimes advancing several meters per year. That motion exerts enormous pressure on underlying terrain. Rock fractures, sediments shift, and existing valleys become deeper. Ice carries debris embedded within it, acting like sandpaper on a continental scale. When imagining the exposed Great Lakes Basin, many of the broad depressions would reflect exactly that process, repeated glacial erosion layered on older geological structures. Before the most recent glaciation, the region likely contained river systems draining toward different directions than today. Some evidence suggests portions of the basin drained south toward the Mississippi system, or northeast toward ancient marine basins. Each glacial advance disrupted those drainage routes, ice-blocked valleys, redirected meltwater, and created temporary lakes that later vanished or shifted location. These transitional lakes left shoreline terraces still visible in some inland areas today. As the last major glacial maximum approached roughly 20,000 years ago, ice thickness over parts of the Great Lakes region may have exceeded a kilometre. That weight depressed the crust beneath it. The land actually sank slightly under the load, a process known as isostatic depression. When ice later melted, the crust began rebounding upward, a movement still measurable today in some northern areas. During glacial retreat, enormous volumes of meltwater accumulated along the ice margin. Temporary proglacial lakes formed where meltwater became trapped between the retreating ice front and higher terrain. These lakes were not identical to the modern Great Lakes. They shifted position repeatedly as ice margins fluctuated. Names like Lake Agassiz, Lake Chicago, and Lake Algonquin appear in geological literature to describe these earlier water bodies. Lake Agassiz, for instance, once covered vast portions of central North America. Though not directly one of the Great Lakes, its meltwater influenced regional drainage patterns significantly. Sudden outbursts of water from proglacial lakes are thought to have affected global ocean circulation and climate patterns. The interconnectedness of freshwater systems and global climate becomes clearer when considering these events. As ice continued retreating, drainage routes stabilized gradually. The basins that would become the Great Lakes began filling more consistently with meltwater and precipitation. Shorelines fluctuated widely during this transition. Ancient beaches, now located well inland, mark stages when water levels stood higher than present. Conversely, submerged terraces beneath current lake surfaces record periods when levels were lower. Glacial sediments contributed heavily to basin shaping. Till, a mixture of clay, sand, gravel and boulders deposited directly by ice, blankets large portions of the region. Outwash plains formed where meltwater streams sorted sediments by size, laying down layered deposits. These materials influence modern soil fertility, groundwater flow, and vegetation patterns across surrounding states and provinces. One often overlooked aspect involves how glaciers influence river capture events. As ice blocked existing drainage paths, water sought new outlets. Rivers sometimes changed direction entirely. This reorganization determined how the interconnected lake system eventually drained toward the Atlantic via the St. Lawrence River, rather than southward as earlier systems may have done. Temperature fluctuations during retreat were not smooth. Cold reversals occasionally halted melting, or even allowed ice to re-advance slightly. Each pause created new sediment ridges, shoreline features, and drainage adjustments. The exposed basin floors in this hypothetical scenario would preserve evidence of these pauses in the form of moraines, sediment fans, and erosional boundaries. Vegetation patterns following ice retreat developed gradually. Initially, tundra-like conditions prevailed near the ice margin. As climate warmed, boreal forests expanded, followed later by mixed deciduous forests in southern portions of the basin. Pollen preserved in lake sediments today allows reconstruction of that ecological succession. Direct access to exposed sediment layers would enhance such reconstructions. Animal migration followed similar patterns. Large mammals including caribou, mastodons, and early bison occupied landscapes emerging from glacial retreat. Fossil remains occasionally appear in sediment deposits around the Great Lakes region. Additional exposures across drained basins might reveal further paleontological evidence of post-glacial ecosystems. Human arrival intersects with this timeline as well. Indigenous populations entered the region thousands of years ago, adapting to changing environments shaped by retreating ice and evolving lake systems. Archaeological sites along ancient shorelines document fishing practices, tool-making, trade networks, and settlement patterns tied closely to freshwater availability. Climate moderation by the lakes developed gradually as water volumes stabilised. Large water bodies absorb heat in summer and release it slowly in winter. This buffering effect created microclimates favourable for agriculture in surrounding areas. Without the lakes, those moderating influences would diminish, illustrating how glacial legacy continues affecting daily life long after the ice disappeared. Sediment cores extracted from current lakebeds provide some of the most continuous environmental records available. Layers accumulate year after year, capturing pollen, dust, volcanic ash, industrial pollutants, and microfossils. These cores act as chronological archives. Exposure of basin floors would allow broader spatial sampling beyond the limited points accessible by drilling from boats. The interplay between glacial erosion and tectonic structure becomes particularly evident when examining Lake Superior. The mid-continent rift provided an initial structural depression. Glaciers deepened it further. Meltwater then filled it. This layered causation explains why Superior is both the largest and deepest of the lakes. Similar though less dramatic interactions shape the other basins. Post-glacial rebound continues to influence shoreline changes today. Northern shores, where ice was thickest, are rising slightly faster than southern shores. This gradual tilting alters relative water levels locally. In a drained scenario, evidence of differential uplift would become more visible across the basin floor through subtle slope variations. Permafrost likely existed near retreating ice margins during early post-glacial periods. As climate warmed, thawing influenced drainage stability and vegetation establishment. Sedimentary structures preserved beneath current lake beds may still contain traces of those permafrost conditions, offering insight into cold climate transitions. Volcanic ash layers occasionally appear in sediment records, carried long distances by atmospheric circulation from eruptions elsewhere on the continent. These ash layers serve as chronological markers because eruption dates are often well established. Exposure of broader sediment surfaces could make such marker layers easier to trace geographically. Water chemistry evolved during lake formation as well. Initial meltwater carried high mineral loads from freshly ground rock. Over time, biological activity, sediment settling, and hydrological cycling stabilised chemical conditions closer to what exists today. These chemical histories influence aquatic ecosystems and drinking water characteristics. The clarity of some Great Lakes waters today partly reflects glacial origin. Low nutrient concentrations and relatively young geological age compared with ancient inland seas contribute to their optical properties. Understanding formation history helps explain why certain ecological dynamics differ from older lake systems elsewhere. Wind-driven wave action began shaping shorelines once open water expanded after glacial retreat. Beaches, dunes, and coastal bluffs developed over thousands of years. Those same features would reappear progressively as water levels declined in this imagined scenario, though now revealing older phases of shoreline development beneath modern ones. Climate variability remains ongoing. While continental ice sheets are unlikely to return under current climate trajectories, smaller glacial advances occurred historically even within the broader warming trend since the last ice age. The Great Lakes themselves continue responding to precipitation patterns, evaporation rates, and temperature shifts year to year. Seeing the basins without water would compress recognition of all these processes into a visible landscape. Terraces, moraines, bedrock ridges, sediment layers, and ancient channels would collectively illustrate how ice, water, and time collaborated to produce the freshwater system now taken for granted. That layered understanding naturally prepares attention for another type of record hidden beneath current waters: One less about ice movement and more about what lived here before the lake stabilised fully. Forests drowned by rising post-glacial waters, fossilised remains preserved in sediment, and biological clues waiting quietly beneath the surfaces that have concealed them for millennia. As the imagined waterline continued slipping outward across the basin floors, another category of hidden evidence would begin appearing, quieter than shipwrecks, older than human settlement, and in many ways more revealing about environmental change. Beneath portions of the Great Lakes lie traces of landscapes that existed before the lakes reached their present extent. These include buried forests, preserved soils, fossil deposits, and organic remains sealed under sediment as water levels rose following glacial retreat. The idea may sound unusual at first, yet it fits neatly with the known sequence of post-glacial events. Ice retreated, meltwater accumulated unevenly, drainage routes shifted, and shorelines advanced and retreated repeatedly before stabilising roughly where they are today. When lakes expand over previously dry land, vegetation becomes submerged. In cold, freshwater conditions with low oxygen availability, decomposition slows dramatically. Tree trunks, roots, leaf litter, and soil layers can remain preserved for thousands of years. Similar submerged forests have already been documented along certain Great Lakes shorelines, where erosion or storms temporarily expose them. Divers sometimes report standing tree stumps visible beneath shallow water. These are not recent growths, but remnants of forests that existed when water levels were lower. In a gradual draining scenario, those preserved forests would begin reappearing in stages. Initially, isolated stumps might protrude from sediment near former shorelines. As exposure progressed, entire patches of ancient forest floor could emerge. Tree trunks, root networks, and soil horizons might remain surprisingly intact, though fragile after long submersion. The preservation would depend heavily on sediment coverage, oxygen exposure, and biological activity once air returned. Species identification from such remains would provide detailed climate information. Tree rings record growth conditions year by year. Wide rings suggest favourable growing seasons. Narrow rings indicate stress, perhaps from drought or cooler temperatures. By analysing ring patterns, dendrochronologists reconstruct past climate variability. Access to submerged forests across large basin areas would expand such datasets significantly. Pollen grains preserved in surrounding sediments add another layer of information. Each plant species produces distinct pollen shapes identifiable under microscopes. Sediment cores extracted from present lakebeds already contain pollen records spanning thousands of years. Exposed sediments would allow broader sampling without reliance solely on drilling from watercraft. Mapping pollen distribution spatially across former basin floors would refine reconstructions of post-glacial vegetation spread. Fossil clues would not be limited to plants. Animal remains occasionally become preserved in waterlogged sediments. Bones of large mammals that roamed post-glacial landscapes could appear where ancient shorelines once existed. Mastodon remains, for example, have been discovered historically in parts of the Great Lakes region. Additional exposures might reveal further specimens, helping paleontologists understand migration routes and habitat preferences during early Holocene periods. Smaller fossils would likely be more abundant. Mollusk shells, fish bones, insect remains, and microfossils such as diatoms accumulate steadily in lake sediments. Diatoms, microscopic algae with silica shells, respond sensitively to water chemistry, temperature and nutrient conditions. Their preserved assemblages allow reconstruction of past aquatic environments. Exposed sediment layers containing diatoms would document transitions from terrestrial to aquatic ecosystems during lake formation. Soil layers buried beneath rising water would attract particular scientific attention. Soils form through complex interactions among climate, vegetation, parent rock material, and time. Preserved paleosols, ancient soils now buried, record environmental conditions at the moment they were submerged. texture, mineral composition, organic content, and fossil root traces all provide clues about vegetation density, precipitation patterns, and seasonal variability. Charcoal fragments within those soils sometimes indicate ancient wildfires. Fire frequency relates closely to climate conditions and vegetation types. Mapping charcoal layers across exposed basin floors could reveal regional fire history spanning thousands of years. Such information contributes to long-term climate models and ecosystem resilience studies. Some buried forests might predate the last full stabilization of lake levels by several millennia. After glaciers retreated, fluctuating meltwater lakes expanded and contracted repeatedly. Forests established during lower water phases were later submerged again. These repeated cycles mean multiple generations of vegetation could be preserved in stacked sediment layers. Exposure would therefore reveal a sequence rather than a single forest horizon. Organic preservation raises interesting chemical considerations. Waterlogged environments often produce peat-like deposits, rich in partially decomposed plant material. Once exposed to oxygen, these materials begin decomposing more rapidly. Scientists would likely document such deposits quickly, before significant deterioration occurred. Conservation strategies sometimes involve controlled reburial or stabilization if preservation holds particular research value. Human cultural history intersects with these biological records as well. Indigenous populations have lived around the Great Lakes region for thousands of years. Early settlements often formed along shorelines because of access to water, fish, and transportation routes. If earlier lower lake faces existed, some archaeological sites could lie beneath present lakebeds. Exposure might reveal stone tools, hearth remains, fishing implements, or habitation evidence from transitional periods when water levels differed from today. Archaeological protocols emphasize careful documentation and respect for cultural heritage. Collaboration with indigenous communities would be essential if such sites appeared. Many oral histories already reference changing shorelines and environmental adaptation. Newly exposed evidence could complement those traditions scientifically, while acknowledging their long-standing significance. The transition from forest to aquatic ecosystem leaves subtle chemical signatures beyond visible fossils. Organic carbon content in sediments often shifts as plant matter decomposes underwater. Stable isotope analysis allows researchers to trace these changes precisely. Exposure of large sediment areas would enable spatial mapping of such chemical transitions, improving understanding of how ecosystems respond when landscapes flood. Insects preserved in waterlogged sediments provide additional climate indicators. Certain beetle species, for example, prefer specific temperature ranges. Fossil insect assemblages help reconstruct seasonal climate conditions during post-glacial periods. Though less visually dramatic than tree stumps, these microfossils carry valuable information. Visual appearance of emerging buried forests would likely be subdued rather than dramatic. Darkened wood, softened by long submersion, would contrast with lighter surrounding sediments. Root systems might remain embedded in former soil layers. Some trunks could still stand upright if sediment support persisted. The scene would resemble a quiet archaeological site more than a living forest. Odor changes might accompany exposure initially. Anaerobic decomposition underwater produces compounds that release characteristic smells when exposed to air. Similar phenomena occur in drained wetlands. These odours usually dissipate as aerobic conditions stabilise and microbial communities adjust. Wildlife response would begin quickly. Birds often investigate newly exposed wetlands for feeding opportunities. Small mammals might colonise stabilised ground. Over time, plant succession would cover exposed organic deposits, integrating them into emerging terrestrial ecosystems. Public interest could focus strongly on visible tree remains because forests are familiar reference points. Seeing trees that once grew where open water now exists challenges intuitive assumptions about landscape permanence. Educational outreach would likely emphasize timelines, explaining how climate shifts, glacial retreat, and hydrological changes produce these transformations gradually. Photographic documentation would capture the contrast between living forests along current shores and fossilised remains farther out across the exposed basin. Such imagery tends to resonate with broader audiences because it makes abstract geological time more tangible. Scientific institutions might establish protected research zones where buried forests appeared extensively. Controlled access would help prevent unintentional damage while allowing systematic study. Similar protections exist at terrestrial fossil forests worldwide. Understanding these preserved ecosystems also informs modern environmental planning. Knowledge of past climate variability helps predict potential future changes. For instance, recognizing how vegetation responded to post-glacial warming offers context for contemporary climate trends. As more biological records surfaced alongside geological ones, the narrative of the Great Lakes would appear increasingly layered. Ice carved the basins. Water filled them. Forests grew, drowned, and left traces. Humans arrived, adapted, navigated, and left artifacts. Each stage remains physically recorded beneath the present surface. Once buried forests and fossil clues became widely visible across the drained basins, attention would naturally shift toward another category of evidence resting beneath the water today, not from deep geological time but from relatively recent human history, settlements, trade routes, and everyday objects that once existed along earlier shorelines before water quietly covered them. As the imagined retreat of the Great Lakes continued beyond ancient forests and fossil-bearing sediments, another layer of history would begin to surface, one tied directly to human presence in the region long before modern cities defined the shoreline. Water has always shaped settlement patterns. People settle near reliable freshwater sources, transportation corridors, fishing grounds, and fertile soil. Because the Great Lakes formed gradually after glacial retreat, shorelines shifted over thousands of years. Earlier human activity often occurred along different lake margins than those seen today. When water levels rose later, some of those sites became submerged, preserved quietly beneath sediments and cold fresh water. Indigenous communities lived around the Great Lakes for millennia before European arrival. These societies maintained complex trade networks, seasonal migration patterns, and cultural traditions closely linked to freshwater ecosystems. Archaeological evidence already exists along current coastlines in the form of fishing camps, tool-making sites, burial grounds, and habitation areas. If the lakes drained gradually in this thought experiment, additional sites once located along earlier shorelines would likely appear farther out across the basin floors. Stone tools often preserve well in submerged environments. Projectile points, scrapers, fishing weights, and grinding stones might emerge where ancient camps once existed. Organic materials such as wood or plant fibres sometimes survive in waterlogged sediments too, especially under low oxygen conditions. That preservation could provide insight into technologies that normally decompose quickly on dry land, such as fishing nets, woven containers, or wooden structures. Trade routes across the Great Lakes region existed long before large sailing vessels arrived. Canoe travel allowed efficient movement of goods and people along interconnected waterways. Copper from the Lake Superior region, chert for tool making, shells from distant coasts, and other materials circulated widely. Submerged portage sites or shoreline camps connected to those routes could become visible as water receded. European exploration beginning in the 17th century added another historical layer. French traders, missionaries, and explorers established posts along lakeshores and connecting rivers. Some early settlements shifted location over time due to flooding, erosion, or changing trade patterns. Exposure of earlier shoreline positions might reveal remnants of temporary trading posts, docks, or defensive structures constructed during those periods. Artifacts from the fur trade era could include metal tools, glass beads used in trade, ceramics, and remnants of wooden buildings. Such objects often hold both archaeological and cultural significance. Collaboration with indigenous communities would remain essential because many items reflect shared histories and living cultural traditions rather than distant past alone. Transportation infrastructure predating modern ports might appear as well. Early piers, breakwaters and landing sites sometimes became obsolete as shipping technology evolved or as shoreline conditions changed. Some were abandoned rather than dismantled. Underwater surveys already document certain examples. Gradual exposure would make them easier to study comprehensively. 19th century industrial expansion introduced another wave of shoreline activity. Lumber mills, mining operations, rail terminals, and early factories often located directly at water's edge for transport efficiency. Environmental regulations were limited at the time, so waste disposal sometimes occurred nearby. Exposed remains of these industrial sites could include foundations, machinery fragments, rail spurs, and discarded materials embedded in sediment. Urban development patterns also shifted repeatedly. Cities such as Chicago, Toronto, Detroit, Cleveland, and Milwaukee expanded outward through land reclamation projects that reshaped coastlines. In some cases, earlier shoreline structures were buried intentionally to create stable foundations for modern construction. Draining the lakes hypothetically would expose parts of those earlier urban phases beyond current waterfronts. Everyday objects often provide the clearest picture of past human life. Bottles, ceramics, tools, clothing accessories, fishing gear, and domestic items occasionally end up in water through accidents or disposal. Freshwater preservation can keep such objects recognizable. Archaeologists frequently emphasize that ordinary items reveal as much about daily life as monumental structures. Fishing traditions themselves leave traces. Indigenous fishing weirs constructed from wood and stone sometimes become submerged when water levels rise. Similar structures have been documented in other lake systems worldwide. If comparable features exist beneath the Great Lakes, exposure could illuminate long-term subsistence strategies tied closely to seasonal fish migrations. Transportation evolution can also be traced through smaller craft remains beyond major shipwrecks already discussed. Canoes, rowboats, early steam launches, and small fishing vessels often operated close to shore. Some were lost during storms or simply abandoned when no longer needed. Their remains contribute to understanding technological adaptation to freshwater navigation. Maps from earlier centuries occasionally show settlements or shoreline features no longer visible today. Comparing those maps with newly exposed terrain would help verify historical records. Cartographic inaccuracies could be corrected and previously uncertain site locations clarified. Historical geography relies heavily on such cross-referencing. Legal considerations would arise quickly once previously submerged historical sites became accessible. Heritage protection laws generally extend to underwater cultural resources. Exposure would shift some responsibilities from maritime heritage agencies to terrestrial archaeological authorities. Binational coordination between Canada and the United States would remain important, because the lakes cross national boundaries. Public interest often intensifies when tangible historical objects appear. Museums might expand exhibits incorporating artifacts recovered responsibly. Educational programs would emphasize context, explaining not only what objects are but how they fit into broader regional history. Responsible stewardship tends to accompany sustained public awareness. Environmental scientists would also examine how human activity affected sediments now exposed. Industrial pollutants, agricultural runoff residues, and urban waste deposits often accumulate in lakebeds. Their distribution reflects historical land use patterns. Studying them provides lessons relevant to modern environmental management. Cultural landscapes involve more than physical artifacts. Place names, oral histories, and community traditions often reference former shorelines, fishing grounds, or travel routes. Newly exposed terrain could validate aspects of those narratives. Such connections reinforce the importance of integrating scientific research with cultural knowledge. Recreational history forms another dimension. Beaches, amusement piers, resorts, and early tourism infrastructure sometimes succumbed to erosion or changing water levels. Remnants of boardwalks, foundations, or recreational equipment could appear. These sites illustrate how people have long interacted with the lakes for leisure as well as livelihood. Military history also intersects occasionally. Coastal fortifications, training facilities, or wartime industrial sites existed in certain locations. Some structures were dismantled, others may have been abandoned as shorelines shifted. Exposure would invite historical reassessment of regional defence and logistics networks. As newly visible human history accumulated across the exposed basin, patterns would emerge. Early indigenous presence near ancient shorelines, European trade routes following navigable waters, industrial expansion aligning with shipping infrastructure, urban growth reshaping coastlines, each phase layered onto the previous one without fully erasing it. This layered human record parallels the geological layering discussed earlier. Ice ages shaped basins, water filled them, forests grew and submerged. People arrived, adapted, built, traded, and sometimes left traces that water later concealed. Exposure would make those overlapping timelines easier to visualize. The presence of historical artifacts also raises conservation challenges. Organic materials preserved underwater can deteriorate rapidly once exposed to air. Archaeologists would prioritize documentation, stabilization, and in some cases controlled reburial. Balancing research access with preservation would require careful planning. Educational outreach could emphasize continuity rather than disruption. The Great Lakes region has always been dynamic. Shorelines shifted after glaciation. Community adapted repeatedly. Recognizing that history may foster perspective on present environmental change discussions. As the expanding, exposed landscape revealed increasing amounts of human historical evidence, attention would inevitably broaden again, this time towards something less culturally dramatic, yet environmentally significant. The industrial and agricultural residues quietly accumulating in lake sediments over the last 2 centuries, materials normally hidden beneath water, but potentially influential once exposed to air and weather. As the imagined retreat of the lakes continued outward, the story would begin shifting from deep geological time and distant human history towards something far more recent and practical. Beneath many areas of the Great Lakes lie sediments that have quietly accumulated residues from industry, agriculture, transportation, and urban growth over the past 2 centuries. These materials are not always visible from the surface today because water acts as a kind of blanket, dispersing some pollutants, burying others, and moderating direct exposure. Removing that water gradually in this hypothetical situation would bring those hidden footprints into clearer view. Industrial development along the Great Lakes expanded rapidly during the 19th and 20th centuries. Steel production, shipbuilding, mining, chemical manufacturing, power generation, and heavy industry clustered along accessible shorelines because water transport reduced shipping costs. Waste management standards at the time were far less strict than modern regulations. Some industrial byproducts entered the lakes through direct discharge, runoff, or atmospheric deposition. Over time, these materials settled into bottom sediments. Sediments act like environmental archives. Fine particles settle slowly, layering year after year. Along with natural materials such as clay, silt, organic debris, and pollen, they capture traces of heavy metals, hydrocarbons, synthetic chemicals, and microscopic plastics. Scientists already study sediment cores to track pollution history. Exposure of larger areas would make those patterns easier to observe spatially, rather than only through isolated sampling points. Heavy metals form one important category. Lead, mercury, cadmium, chromium, and arsenic have all appeared historically in industrial emissions and wastewater. These elements do not degrade chemically. Instead, they bind to sediments. When buried under stable, oxygen-poor conditions, they often remain relatively immobile. Exposure to air, however, can change chemical states, sometimes increasing mobility. Environmental monitoring would therefore become essential during any large-scale sediment exposure. Hydrocarbon residues from fuel spills, shipping activity, and industrial processes represent another component. Oil products tend to bind to fine sediments. Over decades, they break down slowly but can persist in trace amounts. Exposure would not necessarily produce visible oil slicks everywhere, but localized areas near historic industrial centers might show discoloration or odor changes initially. Synthetic organic chemicals add complexity. Polychlorinated biphenols, historically used in electrical equipment and industrial fluids, accumulated widely before regulations restricted their use. Pesticide residues, especially from agricultural runoff, also appear in sediment records. Many of these compounds degrade slowly. Their distribution often reflects historical land use patterns, prevailing winds, and river inflow directions. Microplastics now appear in lake sediments as well. These particles originate from degraded plastic products, textile fibers, tire wear, and packaging materials. They settle gradually through the water column. Exposure of sediments containing microplastics would raise questions about long-term environmental persistence and terrestrial redistribution through wind or runoff. Agricultural runoff contributes nutrients such as nitrogen and phosphorus. These nutrients fuel algae growth in water, but also accumulate in sediments. When exposed, nutrient-rich sediments can initially support rapid plant colonization. However, they may also alter local soil chemistry temporarily until stabilization occurs. Agricultural history around the lakes has therefore left subtle but measurable imprints. Urban wastewater historically carried a mix of household chemicals, pharmaceuticals, and organic waste. Modern treatment systems reduce most contaminants significantly, yet earlier decades saw higher discharge levels. Sediments near major metropolitan areas often reflect that legacy. Exposure would allow direct examination of how urbanization influenced freshwater ecosystems over time. Atmospheric deposition plays a quieter role. Industrial emissions carried by wind settle eventually onto land or water surfaces. Coal combustion historically released mercury and sulfur compounds widely. Even remote parts of the Great Lakes show traces of such deposition. Drained basins might display broad but low concentration distributions reflecting this airborne pathway. Environmental recovery over recent decades deserves recognition alongside past pollution. Binational agreements between Canada and the United States, improved wastewater treatment, emission controls, and conservation initiatives have significantly reduced many contaminant inputs. Sediment records often show declining pollutant concentrations in more recent layers. Exposure would highlight both historical impact and subsequent progress. Ecologically, previously submerged contaminated sediments could influence plant colonization patterns. Some plant species tolerate higher metal concentrations than others. Early vegetation on exposed sediments might therefore reflect underlying chemistry. Ecologists could study succession processes under varying contaminant conditions. Public perception of pollution exposure often involves visible imagery, yet most contamination remains microscopic. Even if sediments appeared visually normal, chemical analysis would still guide environmental management decisions. Clear communication would help prevent misunderstanding while ensuring appropriate caution. Remediation strategies would depend on contamination type and concentration. Options might include stabilization with clean soil cover, controlled revegetation, or targeted removal in high concentration zones. Environmental engineering already addresses similar challenges in smaller drained reservoirs or industrial cleanup projects. Wildlife response would vary. Some birds and mammals might use newly exposed areas quickly. Monitoring would ensure contaminants do not enter food chains at harmful levels. Environmental agencies already conduct such monitoring near known contaminated sites along current shorelines. Legal responsibilities for historical pollution sometimes involve complex jurisdictional questions. Exposure of sediments could renew discussions about liability, remediation funding, and environmental restoration priorities. Existing regulatory frameworks would likely adapt gradually rather than through abrupt policy shifts. Educational opportunities would emerge as well. Visible evidence of industrial legacy provides tangible context for environmental science discussions. Students often grasp pollution dynamics more clearly when they can see layered sediment structures rather than abstract charts alone. Comparisons with other regions offer perspective. Drained lakes elsewhere, such as parts of Central Asia, have revealed contaminated sediments producing dust storms carrying salts and pollutants. The Great Lakes Basin differs climatically and geologically, so outcomes would not necessarily mirror those cases. Nonetheless, lessons from those examples would inform precautionary planning. Water chemistry influences how pollutants behave. Freshwater conditions differ from marine environments in salinity, biological communities, and sediment composition. Studying exposed Great Lakes sediments would refine understanding of contaminant behaviour specifically in large freshwater systems. Technological advances in environmental sensing would assist monitoring. Portable spectrometers, remote sensing drones, and chemical sensors allow rapid assessment across large areas. Such tools already support wetland restoration and contaminated land management projects. Community involvement would likely grow gradually. Local residents often participate in shoreline restoration initiatives today. Similar engagement could occur on newly exposed terrain, combining scientific guidance with volunteer conservation efforts. Climate factors would interact with exposed sediments too. Rainfall patterns, temperature fluctuations, and seasonal freeze-thaw cycles influence erosion and chemical mobility. Long-term monitoring would integrate meteorological data with environmental sampling. The broader lesson from considering pollution exposure lies in recognizing how industrial development and environmental stewardship coexist historically. Early industrial growth rarely prioritized environmental protection because scientific understanding and regulatory frameworks were still developing. Modern awareness reflects accumulated knowledge rather than simple neglect. Seeing sediments without water would visually connect present environmental policy discussions with their historical context. It becomes easier to appreciate why regulations evolved and how ecosystems respond over time when physical evidence is accessible. As this environmental layer joined the geological, biological, and cultural layers already imagined across the drained basins, a more complete picture of the Great Lakes system would form. Natural processes, human activity, climate history, and technological development all leave marks. Exposure would simply make those marks more apparent. And once those industrial and environmental traces became familiar features of the landscape, attention would naturally shift again, this time toward the living systems currently dependent on the water itself, because the gradual disappearance of such a vast freshwater habitat would inevitably reshape ecosystems in ways both immediate and long-term. As the imagined waterline continued retreating across the basin floors, the most immediate and visible transformation would not be geological or historical, it would be biological. The Great Lakes today support one of the largest freshwater ecosystems on Earth. Fish populations, plankton communities, aquatic plants, invertebrates, migratory birds, mammals, and countless microorganisms depend directly or indirectly on the presence of that water. Removing it gradually would not simply reveal land. It would interrupt a complex living network that has developed over thousands of years. Freshwater ecosystems function through layered interactions. At the base are microscopic phytoplankton, algae that use sunlight to produce energy. Zooplankton feed on them. Small fish feed on zooplankton. Larger fish feed on smaller fish. Birds and mammals feed on fish. Nutrients cycle continuously through water, sediment, and living organisms. Temperature gradients and seasonal turnover distribute oxygen, minerals. When water recedes, that entire system begins reorganizing. The earliest biological changes would occur in shallow coastal zones. As water depth decreases, temperature fluctuations become more extreme. Shallow water warms faster in summer and cools faster in autumn. Some species tolerate those shifts better than others. Fish adapted to cooler, deeper water might migrate toward remaining deeper sections. Species already inhabiting nearshore environments would experience habitat compression before full exposure occurs. Wetlands would initially expand outward as water retreats. Marsh plants follow the moving shoreline, colonizing saturated soils. These zones often become temporary refuges for certain species during transition. Amphibians, waterfowl and insects might increase locally for a period as new wetland habitat forms. However, this expansion would be temporary if water continues withdrawing steadily. Deep-water fish species present a different challenge. Lake trout, whitefish, and other cold-adapted species rely on stable temperature layers in deep water. As lake depth decreases, thermal stratification weakens. Oxygen distribution patterns change. If the deepest basins eventually disappear, these species would lose critical habitat entirely unless downstream waterways remain suitable. Migration patterns for birds would adjust gradually. The Great Lakes lie along major North American flyways. Shorebirds use coastal wetlands as resting and feeding sites during seasonal journeys. As shorelines move outward, feeding grounds shift accordingly. Some species are adaptable, following available habitat. Others with more specialized requirements may experience population stress. Aquatic plants would decline as water recedes beyond their tolerance depth. Submerged vegetation stabilizes sediments and provides shelter for fish and invertebrates. Once exposed to air, these plants die back unless capable of adapting to emergent conditions. Their decomposition would initially enrich exposed soils with organic material, potentially accelerating terrestrial plant succession. Invasive species complicate the picture further. Zebra and quagga mussels currently dominate portions of the Great Lakes ecosystem. These mussels attach to hard surfaces underwater, filtering water and altering nutrient cycles. As water disappears, their colonies would perish in exposed areas. Remaining water bodies downstream might still support them, but the overall distribution would contract. Microbial communities, often overlooked, respond quickly to environmental change. Sediment microbes adapted to low oxygen underwater conditions would encounter oxygen-rich air. This shift alters metabolic pathways and chemical cycling. Processes such as nitrogen fixation, methane production, and organic matter decomposition would change accordingly. River systems feeding the lakes would adjust as well. Lower base water levels mean rivers flow farther across exposed basin floors before reaching open water. New channels would carve through sediments. Fish species that migrate between lakes and tributaries for spawning might face altered routes. Some populations could adapt. Others might decline if access becomes restricted. Food webs rarely collapse instantly. They reorganize. As aquatic species diminish in exposed zones, terrestrial species begin colonizing. Grasses, shrubs, and eventually trees establish where soil conditions allow. Insects follow plant growth. Small mammals follow insects and vegetation. Predators follow prey. Over decades, former lakebed might transform into grassland or forest, depending on climate and soil stability. The pace of drainage influences ecological stress significantly. A slow decline allows gradual migration and adaptation. A rapid drop would produce stranded fish populations and abrupt habitat loss. For this thought experiment, imagining a slow transition emphasizes reorganization rather than catastrophe. Water chemistry also changes during retreat. Concentration of dissolved minerals increases slightly in shrinking water bodies due to evaporation and reduced dilution. Some species are sensitive to such shifts. Downstream rivers might experience temporary increases in nutrient load as sediments redistribute. Coastal dunes present another interesting case. Along parts of Lake Michigan, large sand dune systems exist, shaped by wind and wave interaction. As water retreats, new dune formation could occur across exposed sandy sediments. Plant communities specialised for dune environments might expand into these areas gradually. Climate moderation currently provided by the lakes influences surrounding ecosystems indirectly. Without large water bodies storing heat, regional temperature extremes would increase, growing seasons might shorten slightly in some northern areas and lengthen marginally in others depending on complex feedbacks. Such shifts influence plant species distribution across the wider basin. Freshwater mussels and other benthic invertebrates currently inhabit lake bottoms. Exposure would eliminate those populations in drained zones. Some species already face conservation concern due to habitat loss and invasive competition. Their survival would depend on remaining connected water systems. The ecological concept of succession becomes central here. Primary succession occurs on newly exposed substrate lacking established soil. Pioneer species such as lichens and mosses colonize first. They contribute organic matter that gradually forms soil. Secondary succession follows where soil already exists, often proceeding more rapidly. Large portions of exposed lakebed would likely fall into the latter category because sediments contain organic material accumulated over centuries. Wetland birds such as herons, egrets, and waterfowl might initially benefit from expanded shallow feeding grounds. However, as those grounds dry further, they too would shift migration patterns. Long-term population trends would depend on availability of alternative freshwater habitats regionally. Fish hatcheries and conservation programs might attempt to preserve certain economically important species in remaining connected waterways. Fisheries management already adapts to environmental variability. This scenario would simply extend that process on a larger scale. Aquatic mammals in the Great Lakes are limited compared to marine systems, yet species such as otters rely on fish availability. As fish distribution changes, predator territories shift accordingly. Some may migrate along rivers toward downstream habitats. Phytoplankton and algae that currently influence water clarity and nutrient cycles would decline proportionally with water volume. Some species produce harmful algal blooms under certain nutrient conditions. As water decreases, bloom frequency could either intensify in shrinking sections due to concentration or decline as habitat contracts. Human recreational interaction with aquatic ecosystems would change alongside ecological transitions. Fishing communities would adapt, potentially shifting toward river-based or coastal ocean fisheries if viable. Bird watching and terrestrial wildlife observation might increase in newly formed habitats. Soil formation on exposed sediments often involves complex chemical adjustments. Salts dissolved in lake water can crystallize upon drying. In freshwater systems like the Great Lakes, salinity levels are low compared with inland saline lakes, reducing the risk of extensive salt cross formation. Nonetheless, mineral redistribution would influence early plant colonization patterns. The interconnected nature of ecosystems means changes in one layer propagate outward. Decline of aquatic insects affects bird populations. Altered vegetation influences small mammal distribution. Climate feedbacks shape plant succession rates. Observing such transitions across a landscape the size of the Great Lakes Basin would offer rare insight into ecosystem resilience. Environmental management agencies would likely monitor species movement carefully, establishing protected zones where feasible. Wildlife corridors connecting remaining water systems would become important for maintaining biodiversity. Public understanding of ecological complexity often deepens when visible change occurs. Seeing fish populations shift or wetlands migrate reinforces the concept that ecosystems are dynamic rather than static. Educational outreach during such a transformation would emphasize adaptation rather than loss alone. As biological systems reorganized across the exposed basins, the absence of large water surfaces would begin influencing atmospheric processes more noticeably. The lakes currently interact continuously with regional weather patterns, shaping snowfall, rainfall distribution, and seasonal temperature gradients. Without that expansive freshwater surface, those climatic interactions would begin shifting in measurable ways. quietly altering the broader environmental context in which both ecosystems and human communities operate. As the imagined retreat of the lakes continued and aquatic ecosystems gradually reorganized, attention would begin shifting towards something less immediately visible but far-reaching in its effects. Large bodies of water do not simply sit in landscapes. They interact constantly with the atmosphere. The Great Lakes in particular act as enormous heat reservoirs, moisture sources, and stabilizers of regional weather. Removing them, even gradually in this hypothetical scenario, would alter local and regional climate patterns in ways that unfold slowly but steadily. Water has a high heat capacity compared with land. This means it warms more slowly in summer and cools more slowly in winter. The Great Lakes absorb solar energy during warmer months, storing that heat and releasing it gradually as temperatures drop. Coastal regions currently experience milder seasonal transitions partly because of this buffering effect. Without those lakes, temperature swings would likely become more pronounced. Winter conditions around former shorelines would probably grow colder first. At present, lakes release stored warmth into surrounding air during late autumn and early winter. That warmth moderates frost formation, extends growing seasons slightly, and influences snow patterns. As surface area of open water shrank, that moderating influence would weaken. Inland continental air masses would dominate more strongly, bringing colder winter lows. Summer patterns would adjust as well. Water surfaces evaporate steadily, cooling nearby air slightly. Land surfaces heat more rapidly. As exposed basin floors replaced open water, daytime temperatures in surrounding regions might rise modestly. Nighttime cooling could become more rapid because land loses heat faster than water. These changes would not transform the region into an extreme climate zone overnight, but they would shift seasonal averages over time. Lake effect snow offers one of the clearest examples of lake-atmosphere interaction. Cold air moving across relatively warm water picks up moisture. When that air mass reaches land, the moisture condenses and falls as snow, often producing localized heavy snowfall. Cities downwind of the lakes are familiar with these events. As water surfaces diminished, lake effect snow would weaken proportionally. Winter precipitation patterns would become more evenly distributed geographically, rather than concentrated along traditional snow belts. Humidity levels would likely decline slightly near former shorelines. Large water bodies continuously contribute moisture to the atmosphere through evaporation. Reduced evaporation means somewhat drier air masses locally. That could influence vegetation patterns, wildfire risk, and agricultural irrigation needs subtly over decades. Storm formation can also be influenced by large lakes. Temperature differences between water and land create localized pressure gradients that steer wind patterns. Removing the lakes would smooth some of those gradients. Regional wind behavior might shift gradually, affecting everything from coastal erosion patterns to migratory bird flight routes. Fog formation often depends on temperature contrasts between water and air. The Great Lakes regularly produce fog when warm air passes over cooler water or vice versa. Reduced open water would likely decrease fog frequency in certain seasons, altering visibility conditions important for transportation and aviation. Agricultural impacts would follow climate shifts. Many crops grown in the Great Lakes region benefit from moderated temperatures and predictable precipitation patterns. Vineyards near lakeshores, for example, rely on reduced frost risk. Without the lakes, frost dates might shift earlier in autumn and later in spring. Crop selection and planting schedules would adjust gradually in response. Soil moisture dynamics would change too. Lakes influence groundwater levels through hydraulic connectivity. Lower water levels could alter groundwater recharge rates in surrounding areas. Some agricultural zones might require expanded irrigation infrastructure. Others might experience improved drainage depending on local geology. Urban climate effects deserve attention as well. Cities near water often experience slightly moderated heat extremes compared with inland counterparts. Removing the lakes could intensify urban heat island effects modestly. Municipal planning might respond with expanded green spaces reflective building materials, or altered infrastructure designs to compensate. Wildlife migration patterns tied to seasonal climate cues could shift. Some bird species time migrations partly based on temperature gradients influenced by large water bodies. Changes in those gradients might adjust migration timing or routes incrementally. Ice cover on the lakes currently influences winter albedo, the reflectivity of Earth's surface. Snow-covered ice reflects sunlight differently than open water. As lakes disappeared, land surfaces with vegetation or soil would alter reflectivity patterns, feeding back subtly into regional energy balance calculations used in climate modelling. Long-term climate records derived from tree rings, sediment cores, and historical weather data already show the moderating influence of the Great Lakes. Comparing those records with future conditions in this hypothetical scenario would offer valuable data on how large freshwater systems shape continental climates. Evaporation from the lakes contributes to precipitation not only locally, but also downstream. Moisture transported by prevailing winds eventually falls as rain or snow elsewhere. Reducing that moisture source could alter precipitation patterns over broader areas, though exact effects would depend on atmospheric circulation dynamics. Wind fetch, the distance wind travels uninterrupted across water, influences wave formation today. As land replaced water, wind energy would dissipate differently. Dust transport might increase temporarily across exposed sediments until vegetation stabilized surfaces. Similar effects have been observed in smaller drained lake basins globally. Human energy consumption patterns might shift slightly as climate moderation changed. Colder winters could increase heating demand near former shorelines. Warmer summers might raise cooling demand. Energy infrastructure planning typically adapts gradually to such trends. Public perception of climate change sometimes focuses on dramatic global phenomena, yet regional changes often feel more immediate. Observing seasonal weather patterns evolve in tandem with visible landscape change would reinforce understanding of climate system interconnectedness. Hydrological cycles would adjust continuously. Rivers feeding the former lakes would still deliver water downstream, but without large storage basins, seasonal flow variability might increase. Flood control strategies currently benefiting from lake storage capacity would require reassessment. Vegetation distribution across the broader basin might shift slowly as microclimates adjusted. Species at the edge of their tolerance ranges could expand or contract regionally. Ecologists often study such boundary shifts to understand climate sensitivity. Air quality could change subtly as well. Large water surfaces influence atmospheric mixing and pollutant dispersion. Without them, local air circulation patterns might alter slightly, though urban emissions would remain the primary factor. Scientific monitoring networks already track Great Lakes climate interactions extensively. In this thought experiment, those networks would adapt focus toward emerging land-atmosphere interactions. Long-term data sets would become especially valuable for comparing pre- and post-drainage conditions. Despite all these adjustments, continental climate drivers such as latitude, prevailing winds, ocean currents, and solar radiation would continue dominating large-scale patterns. The absence of the lakes would modify regional details rather than completely redefining climate zones. As weather patterns adjusted gradually and ecosystems adapted accordingly, another practical consideration would move into focus. Beyond climate moderation, the Great Lakes currently serve as one of the largest accessible freshwater reservoirs on Earth. Their disappearance would raise questions about water availability, resource management, and the broader implications for human societies accustomed to stable freshwater access across the region. As the imagined disappearance of the Great Lakes continued unfolding in this gradual way, the climatic adjustments would only be part of the larger picture. Another dimension would begin attracting attention steadily, one that extends beyond regional weather or local ecosystems. The Great Lakes collectively hold roughly 1/5 of the world's surface fresh water that is readily accessible. That statistic carries weight not because the water is currently being shipped globally in large quantities, but because it represents stored freshwater stability in a world where water distribution is uneven and increasingly important for agriculture, industry, and population centres. Freshwater differs from other natural resources in one key respect. It cycles continuously, but usable supplies depend heavily on storage systems such as lakes, rivers, aquifers, and seasonal snowpack. Large lakes act as buffers. They smooth out variations in rainfall, snowmelt, and river flow. Without them, water supply becomes more dependent on short-term weather patterns. In this thought experiment, removing the Great Lakes would not eliminate freshwater from the global cycle, but it would redistribute where that water resides and how accessible it remains. Downstream systems would feel the earliest hydrological changes. Increased outflow through connecting rivers during drainage would temporarily boost freshwater discharge into the Atlantic via the St. Lawrence system. Coastal salinity patterns might shift slightly. Estuarine ecosystems, which balance freshwater and saltwater influences, could adjust gradually. Such effects are typically subtle on a global scale, but scientifically interesting because they illustrate how inland freshwater reservoirs influence ocean boundary conditions. Regional water supply infrastructure would require adaptation long before any hypothetical full drainage occurred. Cities such as Chicago, Toronto, Cleveland, Detroit, and Milwaukee rely heavily on the lakes for drinking water. Intake systems extend into open water to ensure stable quality and quantity. As shorelines moved outward, pipelines would need continual extension until eventually alternative sources became more practical. Groundwater would likely become more important regionally. Aquifers surrounding the current lakes already supply water to many communities. However, groundwater recharge patterns partly depend on lake levels and surrounding hydrology. Changes in hydraulic pressure could alter aquifer behaviour gradually. Some wells might yield more water temporarily, others less, depending on local geology. Agriculture across the Great Lakes Basin benefits from reliable freshwater access, moderate climate, and fertile soils shaped by glacial deposits. Without the lakes acting as large storage reservoirs, irrigation planning would shift towards smaller reservoirs, groundwater extraction, or improved water conservation practices. Agricultural adaptation historically occurs through crop selection, irrigation efficiency, and soil management adjustments rather than sudden abandonment of productive regions. Industry historically clustered near the lakes, partly because of water availability for cooling, processing, and transport. Industrial water demand remains significant today, though modern facilities often recycle water more efficiently. In this scenario, industrial planners would gradually transition toward alternative water sources or technologies requiring less water input. Globally, freshwater distribution already shows strong regional contrasts. Some continents possess abundant river systems and lakes, while others rely heavily on seasonal rainfall or groundwater. The hypothetical absence of the Great Lakes would not suddenly create a worldwide shortage, yet it would reduce one of the largest stable freshwater reserves in temperate latitudes. That change would factor into long-term water resource planning discussions. International policy conversations about water security occasionally reference large freshwater basins. Even though large-scale water export from the Great Lakes has historically been limited and regulated, their existence contributes psychological and strategic reassurance regarding North American water availability. Their gradual disappearance would likely stimulate renewed discussion about conservation, infrastructure resilience, and sustainable water use. Hydroelectric power generation along connecting rivers also relies partly on stable lake outflow. Facilities along the St. Lawrence River, for example, generate significant electricity. Altered flow regimes would require operational adjustments. Energy grids generally adapt incrementally to such changes through diversification, rather than relying exclusively on one source. Shipping economics intersect with freshwater availability indirectly. Bulk cargo transport on the lakes currently reduces reliance on long-distance trucking or rail for certain materials. Without navigable lakes, transportation networks would adjust. Rail expansion, pipeline development for certain commodities, and logistical innovation would likely fill the gap gradually. Ecological freshwater functions extend beyond drinking supply. Lakes influence regional humidity, precipitation recycling, and groundwater recharge. These processes contribute to broader hydrological stability. Removing a major reservoir shifts those balances, though atmospheric circulation continues redistributing water globally. One interesting aspect involves how people perceive abundance. Regions with visible large water bodies often develop cultural assumptions of plentiful freshwater. That perception shapes consumption habits, infrastructure design, and conservation attitudes. As visible reservoirs shrink, public awareness of water resource management often increases. Similar patterns have occurred in regions experiencing prolonged drought. Technological innovation frequently follows resource pressure. Improved desalination, wastewater recycling, efficient irrigation systems, and water-saving industrial processes have all advanced partly because of water scarcity concerns in various regions. A gradual Great Lakes reduction would likely stimulate similar technological responses in surrounding areas. Environmental conservation frameworks would emphasize watershed protection more strongly. Rivers feeding the former lakes would become primary freshwater arteries. Protecting their quality and flow would gain prominence. Watershed management already exists, but its importance would become more widely recognized. Freshwater ecosystems elsewhere might experience indirect benefits or pressures. Migratory bird routes, fish trade patterns, and agricultural supply chains could adjust. Global interconnectedness means regional environmental changes rarely remain isolated indefinitely. Climate modelling also incorporates large freshwater bodies because they influence evaporation, albedo, and atmospheric circulation. Removing such a significant reservoir would provide a natural experiment for scientists studying climate-water feedback loops. Long-term data sets comparing pre- and post-drainage conditions would inform broader climate science. Public health considerations would remain central. Reliable clean water supply underpins sanitation, disease prevention, and food production. Infrastructure adaptation would prioritise maintaining those standards even as natural storage systems changed. Cultural identity tied to freshwater landscapes would evolve gradually. Communities that historically defined themselves by lakefront living, maritime trade, or coastal recreation would reinterpret those identities. Similar transitions have occurred in regions where rivers changed course or shorelines shifted over historical timescales. Economic diversification often accompanies environmental change. Regions once dependent on a particular natural resource frequently develop alternative industries over time. Tourism, technology, education, renewable energy, and service sectors might expand to balance reduced lake-dependent industries. Scientific collaboration across borders would remain essential. The Great Lakes Basin already involves coordinated research between Canada and the United States. Addressing large-scale freshwater redistribution would likely strengthen those partnerships rather than weaken them. Water law frameworks tend to evolve slowly, shaped by precedent, treaties, and practical necessity. Existing agreements governing Great Lakes water use would adapt gradually to new hydrological realities. Legal stability often supports environmental management continuity. Despite the scale of the hypothetical loss, Earth's overall hydrological cycle would continue. Ocean evaporation, precipitation, river flow, glacier melt, and groundwater movement operate globally. The disappearance of one major freshwater reservoir changes distribution, not the existence of water itself. Understanding that distinction helps maintain perspective. Large lakes appear permanent within human lifetimes, yet geological history shows that lakes form, expand, shrink, and sometimes vanish over millennia. Human systems adapt alongside those changes, usually through incremental adjustment rather than abrupt transformation. As the freshwater reservoir dimension became clearer, another practical aspect would begin drawing attention: Geography itself would change subtly but persistently. Borders, transportation routes, economic zones, and regional relationships shaped by the lake's presence would gradually adjust as exposed land replaced open water, creating new connections and redefining old ones. As the imagined retreat of the Great Lakes continued and the freshwater implications settled into long-term planning conversations, another transformation would begin attracting steady attention. Geography, the kind that appears stable on maps for generations, would gradually shift. Borders, transportation networks, economic zones, and everyday patterns of movement have all developed with the lakes in place. Removing them slowly would not redraw political lines overnight, but it would quietly change how those lines function in practice. The international boundary between Canada and the United States currently follows portions of the Great Lakes system. Treaties establish those boundaries using navigable channels, islands, and midpoints in open water. As water receded, the legal definition of those boundaries would likely remain unchanged initially. However, the physical reality beneath them would transform. Former open water borders might become stretches of land separated by administrative jurisdiction rather than water. Such changes are not unprecedented. River boundaries worldwide shift naturally through erosion, sediment deposition, and seasonal flooding. Legal frameworks often distinguish between gradual change and sudden channel shifts. A slow lake retreat in this thought experiment would probably be treated similarly, maintaining treaty boundaries while adapting administrative practices to new terrain. Transportation networks would evolve in parallel. Today, ferries, shipping lanes, and port infrastructure connect cities across the lakes. Without water barriers, land routes would expand. Highways, rail corridors, and possibly pipelines could cross former lakebeds where engineering conditions permit. Some connections that currently require long detours around lake shores might become more direct over newly exposed terrain. Economic geography tends to follow transportation efficiency. Cities historically positioned as port hubs might diversify further into logistics, manufacturing, or service industries connected by land routes. Conversely, communities once separated by water might find closer economic integration as travel distances shorten. Trade patterns rarely remain static when physical connectivity changes. Ports themselves would transition gradually. Existing harbour infrastructure would either extend outward, following receding water, or eventually repurpose entirely. Some former ports might become inland logistics centres. Others could shift toward tourism, research, or conservation roles depending on local priorities. Adaptation usually reflects both economic opportunity and cultural identity. Natural resources beneath the former lakebeds might draw interest. Geological surveys already map mineral potential under certain parts of the basin. However, extraction decisions depend on environmental impact, economic feasibility, and regulatory frameworks. Newly exposed land would likely undergo extensive assessment before any development proceeded. Land ownership questions would arise steadily. Newly exposed terrain does not automatically fall into simple ownership categories. Governments, indigenous nations, municipalities, and private stakeholders might all have legitimate claims depending on historical treaties, property law, and environmental statutes. Negotiation processes would emphasize clarity and cooperation to avoid conflict. Indigenous sovereignty considerations would be especially important. Many treaties reference land and water use rights tied to traditional territories around the lakes. Exposure of new land could intersect with those agreements. Collaborative governance models increasingly recognize Indigenous leadership in environmental stewardship, suggesting such conversations would emphasize partnership rather than unilateral decisions. Agricultural potential might attract attention as soils stabilized. Lake sediments often contain fine mineral particles and organic matter, potentially creating fertile conditions once drainage and soil structure develop adequately. However, initial soil stability, contaminant levels, and water availability would determine suitability. Agricultural expansion would likely occur cautiously and incrementally. Urban planning would respond gradually. Some cities might expand toward newly exposed areas if infrastructure, environmental assessment, and economic rationale supported development. Others might designate large portions as conservation zones, wetlands, or recreational spaces. Planning philosophy often reflects regional values and environmental priorities. Tourism patterns would evolve along with geography. Coastal tourism today focuses on beaches, boating, fishing, and waterfront recreation. Former lakebeds might attract visitors interested in geology, ecology, history, or simply novel landscapes. Tourism industries often adapt creatively when environments change, incorporating education, conservation, and cultural heritage elements. Cross-border cooperation would remain essential. Environmental monitoring, infrastructure development, and economic planning rarely stop at political boundaries in shared ecosystems. The Great Lakes already serve as a model for binational collaboration through agreements addressing water quality, fisheries management, and environmental protection. Those collaborative structures would likely continue adapting. Cultural identity tied to lakefront living would evolve gradually rather than disappear. Communities historically shaped by maritime culture often reinterpret that heritage when environmental conditions shift. Museums, festivals, educational programs, and local narratives preserve continuity even as landscapes change. Energy infrastructure might shift location as well. Power plants currently located near water for cooling could adapt to alternative cooling technologies or relocate closer to new water sources. Renewable energy projects such as wind farms might expand across open terrain if environmental assessments supported development. Insurance, zoning, and real estate markets would adjust slowly. Waterfront property classifications would change, flood risk models would update, infrastructure investments would reflect new environmental conditions. These processes typically unfold over decades rather than years. Scientific mapping would intensify during geographical transition. High-resolution satellite imagery, aerial surveys, and ground-based measurements would document emerging landforms continuously. Updated maps would guide infrastructure planning, environmental protection, and navigation adjustments in remaining waterways. Transportation history often shows that routes follow least resistance. Water once provided efficient movement corridors. Land routes replacing them would seek similarly efficient paths, influenced by terrain, soil stability, and environmental protection considerations. Public perception of distance might shift subtly. Cities once separated by wide water expanses would feel geographically closer if direct land routes developed. Cultural exchange, commuting patterns, and economic partnerships could strengthen accordingly. Environmental restoration opportunities might emerge. Wetlands, grasslands, or reforested areas on former lakebeds could enhance biodiversity, carbon sequestration, and recreational access. Conservation planning often integrates ecological function with human use. Legal education and policy research would likely examine this transformation closely. Boundary law, environmental governance, water rights, and land use planning all intersect in complex ways when major geographical features change gradually. International trade logistics might also adapt. Bulk commodities currently shipped via the lakes could transition more heavily to rail or road. Economic efficiency calculations would determine optimal transport methods over time. Social adaptation typically follows environmental change through incremental adjustments in lifestyle, employment, and cultural expression. People tend to reinterpret landscapes rather than abandon them entirely. Historical examples worldwide show resilience when environmental transitions occur gradually. Communication infrastructure might expand across newly exposed terrain as well. Fiber optic cables, pipelines, power lines, and transportation corridors often follow accessible routes. Former lakebeds could offer relatively flat pathways once stabilized. Educational institutions would incorporate evolving geography into curricula. Students living near former shorelines would grow up with a different mental map than previous generations. Geography education continually reflects current environmental realities. Through all these changes, continuity remains as important as transformation. Rivers would still flow, seasonal weather cycles would continue, communities would adapt, often creatively, integrating new landscapes into familiar social and economic frameworks. And as those new land connections settled into everyday experience, another sensory dimension of change would begin becoming noticeable, something less discussed in maps or policy documents but deeply tied to human perception: the shift in sound, atmosphere, and ambient environment. Once vast open water surfaces no longer shape the acoustic and sensory character of the region. As the imagined retreat of the Great Lakes continued and new land gradually replaced open water, one of the more subtle yet deeply perceptible changes would begin unfolding quietly. Beyond shifts in climate, ecology, and geography, the soundscape itself would transform. Large bodies of water shape how regions sound as much as how they look. Waves, wind across open surfaces, distant ship engines, harbour activity, and the soft, continuous motion of water against shorelines all contribute to a constant background layer of sound that many residents barely notice until it is absent. Water behaves differently than land when it comes to acoustics. Sound travels efficiently across open water with minimal obstruction. Low-frequency noise, such as distant ship engines or foghorns, can carry surprisingly far. Waves breaking along rocky coasts produce rhythmic patterns that become part of a region's sensory identity. As open water receded in this thought experiment, that entire acoustic layer would gradually thin and then disappear. Initially, the change might feel subtle, a slightly quieter shoreline at night. Fewer wave patterns during windy days because fetch distance, the uninterrupted stretch of water across which wind travels, would shorten as the lakes shrank. Reduced fetch means smaller waves. Smaller waves mean less shoreline impact noise. Over time, what once felt like background ambience would fade into occasional memory. Harbours and ports currently generate steady sound activity. Docked vessels hum quietly as onboard systems operate. Cranes move cargo, buoys clink against hulls. Maritime communication signals punctuate foggy mornings. As water levels dropped and shipping routes shifted, these sounds would relocate or diminish. Former port cities might notice an unfamiliar stillness along waterfront districts. Wind interaction would also change character. Today, wind moving across water creates a distinct low, continuous tone, sometimes described as a distant rushing sound. When that same wind passes over exposed sediment or newly forming vegetation, it produces different textures. Grass rustles, dry soil shifts softly. The tonal quality changes from fluid to granular. Residents attuned to environmental sound would detect that transition, even if unable to describe it immediately. Bird calls would shift as well. Seagulls, terns, and other water-associated species produce distinct coastal soundscapes. As aquatic habitats shrink, those species would relocate. In their place, terrestrial birds would gradually dominate. Songbirds, meadowlarks, and other grassland species might fill the acoustic space once occupied by lake-dependent wildlife. Foghorns, historically important for maritime navigation, would fall silent permanently. Their long, resonant tones often carry for miles over open water. Without shipping lanes, such signals would become historical artifacts rather than active tools. Maritime museums might preserve recordings, but the living experience of hearing a foghorn roll across a cold autumn evening would fade. Ice sounds would vanish too. During winter, expanding and contracting ice sheets on the lakes produce cracking, booming, and grinding noises. These sounds sometimes travel through shoreline neighbourhoods on particularly cold nights. Without broad ice formation across open water, that seasonal acoustic phenomenon would disappear. Storm acoustics would alter significantly. Currently, strong winds generate wave crashes, spray and structural vibrations in coastal infrastructure. Storms over land produce different sound signatures: branches snapping, debris moving, rain hitting varied surfaces. As water disappears, storm sounds would shift from wave-dominated to land-dominated patterns. Human recreation contributes its own layer to the lake's soundscape. Motorboats, sailboats, fishing activity, beach gatherings and water sports create seasonal acoustic rhythms. Summer weekends near the shore often include engine hums and distant laughter carried across water. As recreational use transitioned toward land-based activities, those patterns would change accordingly. There is also a psychological dimension to sound absence. Continuous natural sounds often create a sense of space and openness. The low, steady presence of waves can mask other urban noises, functioning almost like natural white noise. Removing that layer might make certain inland sounds more noticeable. Highway traffic, industrial activity, or even wind through buildings. Acoustic ecologists study how landscapes influence sound distribution. Water reflects sound differently than soil or vegetation. Exposed basin floors, especially if initially flat and sparsely vegetated, might create unusual echo patterns. Open terrain can carry sound long distances without the dampening effect of trees or buildings. Residents might notice that certain noises travel farther across the exposed plains until vegetation density increases. Wildlife communication relies heavily on acoustic cues. Frogs calling in wetlands, fish generating low-frequency sounds underwater, and insects buzzing near shore all contribute to current auditory complexity. As ecosystems reorganized, communication networks among species would adapt. New species combinations would produce new acoustic patterns. Nighttime sound might feel particularly different. Currently, gentle wave action persists even after human activity quiets. Without it, nighttime near former shorelines might feel more silent, or punctuated only by wind and distant terrestrial wildlife. Such sensory shifts often influence emotional perception of place. Cultural memory preserves environmental sound strongly. People who grew up near the lakes often associate particular sounds with specific seasons or moods. The rhythmic splash against docks, the creaking of moored boats, or the hollow resonance of wind across frozen water form part of regional identity. As those sounds faded, nostalgia might accompany the transition. Technological sound mapping could document these changes systematically. Acoustic sensors placed across shrinking shorelines would record gradual shifts in frequency patterns over years. Comparing recordings before and after exposure would provide a rare dataset of landscape-scale acoustic transformation. Even industrial noise patterns would adjust. Many lakeside facilities rely on water for cooling, transport or processing. As operations relocate or redesign, associated sound emissions would move with them. Some areas might grow quieter, others could experience increased terrestrial transport noise. Wind turbines or renewable energy installations across exposed terrain might introduce new acoustic elements if development occurred. Infrastructure decisions would therefore influence long-term soundscapes significantly. Seasonal festivals and cultural events tied to waterfront settings would likely adapt their auditory character as well. Music festivals once positioned beside open water might relocate inland. Acoustic dynamics in open plains differ from those near water, altering how sound carries and resonates. Environmental psychology research suggests that natural water sounds contribute to perceived calmness and stress reduction. The absence of such sounds might subtly affect how people experience relaxation or recreation near former lakebeds. New sensory cues would eventually replace old ones, but the transition period could feel unfamiliar. Dust movement across newly exposed sediments during dry periods might introduce soft rustling sounds distinct from wave action. As vegetation stabilized surfaces, wind would produce grassy, swaying tones rather than sediment shifting. The combination of these acoustic changes would gradually redefine how the region feels on a sensory level. Even if visual adaptation occurred quickly, sound often lingers longer in memory. People might comment that something feels different without immediately identifying why, until they realise the absence of steady water movement in the background. Over time, the new soundscape would normalise. Children growing up after the transition would associate wind across grasslands, birdsong, and distant land traffic with their environment rather than waves and harbour signals. Cultural identity would adjust accordingly. As the auditory character of the region settled into its new form, attention would likely turn toward a less measurable but equally significant dimension of change: the psychological response of individuals and communities confronted with the disappearance of a landscape feature long considered permanent, and how collective memory, attachment and identity evolve when familiar horizons quietly shift. As the imagined retreat of the Great Lakes continued and the physical environment kept shifting in these gradual, almost patient ways, the next layer of change would not lie in geology, ecology, or climate. It would unfold inside people's perceptions. Large natural landmarks do more than shape maps or ecosystems. They quietly shape identity, memory, routine, and emotional orientation. When a feature as vast and historically stable as the Great Lakes begins disappearing, even slowly, the psychological response tends to be complex rather than dramatic. Adaptation usually arrives through small adjustments in how people interpret familiar surroundings. Landmarks function as anchors. People orient themselves spatially and emotionally around stable reference points. A shoreline is not just where land meets water, it becomes part of daily mental geography. Residents know where the sun rises relative to the lake, how storms approach, where recreational spaces lie, how seasons feel along the water. As the shoreline moved outward gradually in this thought experiment, those familiar cues would shift little by little. No single moment would feel transformational, yet cumulative change would subtly reshape orientation. Memory plays a large role here. Individuals often store personal experiences in relation to landscapes. Childhood visits to beaches, family fishing traditions, evening walks along waterfronts, or simply habitual commuting routes near the lakes form mental associations. When the landscape changes, those memories remain but detach slightly from current surroundings. People might find themselves recalling how something once looked even while standing in a place that now appears different. This phenomenon is not unique to lakes. Similar responses occur when rivers change course, glaciers retreat, forests burn and regrow, or coastlines erode. Psychologists sometimes describe this as environmental memory persistence. The brain maintains a stable internal model of familiar surroundings even as external reality evolves. Adjustment happens gradually as new sensory information accumulates. Community identity would shift as well. Many Great Lakes cities incorporate the lakes into their cultural self-description. Tourism branding, sports team names, local art, cuisine traditions and regional storytelling all reference freshwater identity. As water disappeared, communities would reinterpret that identity rather than abandon it. Historical continuity often remains important even when physical context changes. Nostalgia would likely emerge quietly. Not necessarily sadness, but reflective awareness that something long familiar has transformed. Photographs, recordings, family stories, and cultural artifacts would preserve earlier landscapes. Museums and archives might document shoreline evolution, creating collective memory repositories. Psychological research shows that humans adapt surprisingly well to gradual environmental change. Abrupt disruptions tend to produce stronger stress responses. Slow transformations allow time for cognitive reframing. People begin incorporating the new normal into daily expectations without conscious decision. That gradual adaptation would probably characterize the Great Lakes scenario as well. Economic identity intertwines with psychological perception too. Regions historically associated with shipping, fishing, or waterfront recreation would develop alternative economic narratives. People often derive a sense of purpose and belonging from regional industries. Transitioning industries, therefore, involves both practical and emotional adjustment. There is also the concept of place attachment. Environmental psychologists study how individuals form emotional bonds with specific locations. Water bodies often enhance place attachment because of aesthetic value, recreational opportunities, and cultural symbolism. As lakes receded, attachment would shift toward new features, emerging wetlands, grasslands, geological formations, or historical sites revealed by exposure. Generational perspective matters. Older residents might retain vivid memories of full lakes. Younger generations growing up during or after the transition would treat exposed landscapes as ordinary. Cultural narratives often bridge those perspectives, integrating past and present into shared identity rather than conflict. Education would influence adaptation strongly. Schools incorporating environmental change into curricula help normalize evolving landscapes. Understanding geological time, climate dynamics, and ecosystem adaptation provides context that reduces uncertainty. Knowledge tends to replace speculation with perspective. Social cohesion often strengthens during shared environmental transitions. Communities collaborate on planning, conservation, economic diversification, and cultural preservation. Cooperative responses tend to mitigate anxiety associated with environmental change. Media portrayal plays a role as well. Calm, factual communication supports steady adaptation. Sensational framing can amplify concern unnecessarily. Public trust in scientific institutions and transparent policy processes contributes to psychological stability. The visual horizon itself influences perception. Large water bodies create expansive sightlines. Their disappearance would introduce more textured landscapes, perhaps rolling plains or emerging vegetation patterns. Humans often respond differently to enclosed versus open visual environments. Some might find new landscapes more intimate. Others might miss the visual openness water provided. Recreation patterns would shift emotionally as well as physically. Activities tied to water carry sensory associations. Sounds of waves, reflections of sunlight, seasonal ice patterns. New recreational forms would develop around emerging landforms. Hiking, wildlife observation, historical exploration, or agriculture-related tourism could fill similar social roles. Spiritual and symbolic meanings attached to water deserve attention too. Many cultures view large water bodies as symbols of continuity, renewal, or connection. As physical water receded, symbolic interpretations might evolve rather than disappear. Cultural traditions often adapt symbolism to new contexts. Urban design might intentionally preserve visual or symbolic connections to former shorelines. Parks, monuments, or interpretive trails marking historical water levels could maintain continuity between past and present landscapes. Such design choices support collective memory. Mental mapping, the internal spatial representation people use for navigation, would update incrementally. Navigation apps, signage, and infrastructure planning would reinforce new geography. Over time, mental maps align naturally with updated physical reality. Psychological resilience research consistently shows that people cope best when change is understandable, gradual, and accompanied by visible adaptation pathways. This thought experiment assumes gradual change, which tends to favour resilience rather than distress. Artistic expression would likely reflect the transition. Literature, photography, film, and visual art often explore environmental change through personal narrative. Creative work helps communities process transformation emotionally. Economic opportunity perception influences psychological response. If emerging landscapes create new industries or recreational opportunities, optimism often balances nostalgia. Human adaptation historically combines preservation of memory with exploration of possibility. There may also be periods of uncertainty while infrastructure, legal frameworks and environmental management strategies evolve. Clear communication from institutions helps maintain public confidence during such transitions. Cognitive flexibility plays an important role. People capable of reframing change as evolution rather than loss tend to adapt more comfortably. Education, community support, and cultural narratives all contribute to that flexibility. As collective perception adjusted and new identities formed around evolving landscapes, scientific curiosity would continue expanding alongside emotional adaptation. The newly exposed terrain would offer unprecedented opportunities for research, observation, and discovery, turning what began as a hypothetical environmental shift into an ongoing scientific laboratory where multiple disciplines could study long-term environmental processes directly. As the imagined retreat of the Great Lakes continued and communities gradually adjusted to shifting geography, ecosystems, and climate patterns, scientific interest would expand steadily rather than suddenly. Large environmental transitions tend to attract researchers from multiple disciplines because they offer rare chances to observe processes that usually unfold either underwater, underground, or across timescales too long for direct observation. The gradual exposure of such an enormous freshwater basin would effectively create an open-air laboratory extending across thousands of square kilometres, allowing investigation of geology, ecology, archaeology, hydrology, climate science, and environmental chemistry simultaneously. Geologists would likely arrive first in large numbers, partly because newly exposed bedrock and sediment layers provide direct evidence of long-term Earth processes. While sonar mapping and sediment cores already offer valuable information, nothing replaces direct physical access. Researchers could walk along glacial striations, examine moraine structures continuously rather than through isolated drill samples, and study fault lines or rift-related formations without water obscuring fine details. Continuous exposure across wide areas improves understanding of how ice sheets sculpted the continent and how tectonic structures guided basin formation. Sedimentologists would focus closely on layered deposits across the former lake floors. Each layer represents a specific period of environmental conditions. Thickness, grain size, mineral content, and biological traces reveal information about past water levels, erosion rates, climate variability, and human influence. Mapping these layers laterally across large areas helps reconstruct environmental history more precisely than isolated cores. It allows researchers to see how events such as floods, drought periods, industrial pollution phases, or volcanic ash deposition spread across the basin. Paleoclimatologists would find particular value in those sediment exposures. Pollen grains preserved in sediment record vegetation patterns over thousands of years. Different plant species dominate under different climate conditions. By analysing pollen distribution across exposed layers, scientists could reconstruct regional temperature and precipitation trends extending back to the end of the last ice age. Such long-term data sets help refine climate models that guide modern environmental planning. Archaeologists would also move quickly to document human history revealed beneath former waters. Early indigenous settlements along shifting post-glacial shorelines might appear farther out than previously expected. Trade routes, fishing sites, tool-making areas, and habitation remains would offer insight into how early populations adapted to environmental change. Careful collaboration with indigenous communities would remain central to interpretation, ensuring cultural context accompanies scientific analysis. Maritime archaeologists, already experienced in underwater exploration, would adapt methods for land-based preservation of shipwrecks and harbour infrastructure. Documenting vessel construction techniques across centuries becomes easier when full structures are accessible without diving operations. Cargo analysis might reveal economic trends, technological development, and regional trade connections in ways historical records alone cannot capture. Ecologists would monitor biological succession closely. exposed sediments rarely remain barren for long. Microorganisms colonize first, followed by pioneer plants, insects, birds, and eventually more complex ecosystems. Observing how life establishes itself across such a vast area provides insight into resilience, soil formation, nutrient cycling, and habitat development. These observations could inform restoration projects in other regions experiencing environmental disturbance. Soil scientists would examine how former lake sediments transition into terrestrial soils. Soil formation involves physical weathering, organic matter accumulation, microbial activity, and water drainage patterns. Understanding how quickly fertile soil develops on exposed freshwater sediments has implications for agriculture, conservation, and land management planning. Hydrologists would study groundwater interactions extensively. Lakes exert pressure on surrounding aquifers. As water levels dropped, groundwater flow patterns would adjust. Springs might appear in new locations. Some wetlands could form where groundwater intersects exposed surfaces. Monitoring these processes helps improve regional water resource management and predictive hydrological modelling. Environmental chemists would focus on contaminant behaviour once sediments previously submerged became exposed to oxygen. Chemical stability often changes under different environmental conditions. Metals may oxidize, organic pollutants may degrade faster, and nutrient cycling patterns may shift. Understanding these transitions supports environmental remediation strategies and public health planning. Atmospheric scientists would observe how removal of large water surfaces affects local weather patterns directly. Measurements of evaporation rates, temperature fluctuations, humidity changes, and wind dynamics across former lakebeds would refine climate models. Most current models rely on indirect data. Direct observation across a basin of this scale would provide valuable calibration points. Biologists specializing in freshwater species would monitor how aquatic populations redistribute. Fish migration downstream, adaptation of wetland species, and changes in plankton communities offer insight into ecosystem flexibility. Such studies contribute to broader conservation biology knowledge applicable worldwide. Remote sensing specialists would deploy satellites, drones, and ground-based sensors to track landscape evolution continuously. High-resolution imagery helps map vegetation spread, erosion patterns, soil moisture changes, and infrastructure adaptation. Combining remote sensing with ground observations produces comprehensive environmental data sets. Geomorphologists would analyze how wind and water reshape newly exposed terrain. Even after major drainage, rainfall, river inflow, and seasonal freeze-thaw cycles continue sculpting landscapes. Dune formation, channel incision, slope stabilization, and sediment transport become observable in real time rather than inferred retrospectively. Public health researchers might examine how environmental change influences human well-being indirectly. Air quality changes, new recreational patterns, altered food sources, and economic adaptation all interact with public health outcomes. Monitoring these factors helps communities adapt effectively. Economists would study regional adaptation patterns as industries adjust. Transportation logistics, agriculture, tourism, energy production, and urban development all respond to environmental context. Understanding economic resilience contributes to broader policy planning. Legal scholars and policy researchers would analyze governance challenges associated with emerging land, water rights adjustments, and cross-border coordination. Environmental law often evolves alongside physical landscape changes, providing case studies for international cooperation. Educational institutions would likely establish long-term field stations across exposed areas. Such stations support interdisciplinary research, student training, and public outreach. The opportunity to study large-scale environmental transition directly tends to attract sustained academic interest. Technological innovation often accelerates when new research environments emerge. Improved portable sensors, data analysis techniques, environmental monitoring platforms, and conservation technologies could develop in response to the unique conditions presented by the exposed basin. Cultural researchers and anthropologists would document how communities reinterpret identity during environmental transformation. Oral histories, artistic expression, and social adaptation patterns provide insight into human resilience and cultural continuity. Energy researchers might explore renewable resource potential across newly exposed terrain, evaluating wind patterns, solar exposure, and infrastructure feasibility while balancing environmental conservation concerns. Long-term ecological monitoring programs would likely extend for decades. Environmental transitions rarely conclude quickly. Continuous data collection helps identify trends, unexpected feedback loops, and emerging challenges. Comparative studies with other regions experiencing lake shrinkage or environmental change would benefit from this large-scale example. Lessons learned could apply globally, particularly in areas facing water scarcity or climate-driven landscape shifts. The interdisciplinary nature of such research would encourage collaboration among scientists who rarely work together directly. Geologists, ecologists, economists, sociologists, engineers, and policymakers would share data and perspectives, strengthening integrated environmental understanding. Public engagement often increases when scientific research occurs visibly within local landscapes. Community science initiatives, educational tours, and open data platforms might help residents participate in observation and learning. Over time, the exposed basin would become one of the most intensively studied environmental regions on Earth, not because of crisis alone, but because of the rare chance to observe interconnected Earth systems adjusting in real time. A process that naturally leads toward the next question. Scientists would continue asking quietly in the background whether conditions capable of producing such a transformation could ever occur naturally at all, or whether the scenario remains purely hypothetical within current geological and climatic understanding. As the imagined exposure of the Great Lakes continued through all these geological, ecological, historical, and social layers, one question would eventually begin surfacing more frequently. After exploring what might be revealed, people naturally start wondering whether such a transformation could ever occur outside imagination. The answer, approached calmly and scientifically, is that under present Earth conditions, the complete draining of the Great Lakes remains extremely unlikely. Still, examining why that is the case helps clarify how stable large freshwater systems actually are, and what kinds of forces would be required to alter them significantly. To begin with, the Great Lakes exist because of a very specific combination of geological structure, glacial history, and ongoing hydrological balance. Their basins were carved partly by ancient tectonic features, then deepened by continental glaciers, and finally filled by meltwater, precipitation, and river inflow. That balance continues today. Rivers feed the lakes continuously. Precipitation adds water. Evaporation removes some. Outflow through connecting rivers maintains equilibrium. Unless one of those major inputs or structural constraints change dramatically, the lakes remain stable over human timescales. Natural evaporation alone cannot realistically drain them. The surface area is large, yet the water volume is enormous. Seasonal evaporation already occurs, especially during warmer months, but precipitation and river inflow typically compensate over time. Climate fluctuations can raise or lower lake levels temporarily, sometimes noticeably over decades, but not to the extent of eliminating entire basins. Geological records show fluctuations, not disappearance. Diversion through rivers also has natural limits. The Great Lakes system drains primarily through the St. Lawrence River. That outlet sits at a defined elevation relative to the lake basins. Water cannot drain below the level of its outlet without a new lower outlet forming. Creating such an outlet naturally would require major geological change, such as tectonic uplift in one area or erosion breaching a lower pathway elsewhere. Neither process operates quickly in this region. Tectonic activity around the Great Lakes Basin remains relatively low, compared with plate boundary zones. Earthquakes occur, occasionally but generally at moderate magnitudes, insufficient to fracture continental crust deeply enough to create new drainage routes. The mid-continent rift underlying Lake Superior is ancient and inactive. While structural features persist, they are not actively opening in ways that would allow rapid water escape. Glacial processes once reshaped the basin dramatically, so it is reasonable to ask whether future glaciations could alter the lakes again. Ice ages do operate on long cycles. If large continental glaciers return tens of thousands of years in the future, they could theoretically modify basin structure, redirect drainage, or cover the lakes entirely with ice. Even then, complete drainage would not be guaranteed. More likely outcomes would involve altered shorelines, new proglacial lakes, or temporary ice-covered freshwater storage. Climate change discussions sometimes raise concerns about long-term drying trends. Warmer temperatures increase evaporation rates, yet they can also increase precipitation depending on atmospheric circulation patterns. Current climate models do not project conditions that would evaporate the Great Lakes entirely. Level fluctuations are possible. Disappearance is not considered plausible within foreseeable climate scenarios. Human engineering occasionally prompts speculation as well. Large dams, diversions, or canal systems have reshaped smaller lakes globally. However, the scale of the Great Lakes makes deliberate drainage impractical economically, environmentally, and politically. International agreements between Canada and the United States specifically protect the lakes from large-scale diversion. Engineering projects affecting them undergo extensive scrutiny. Catastrophic scenarios sometimes appear in fiction, such as meteor impacts or extreme tectonic collapse. While such events are theoretically possible anywhere on Earth, they fall outside realistic planning considerations. Planetary scale impacts would produce global consequences far beyond any single lake system. Scientific assessment focuses instead on processes consistent with known geological behaviour. One natural factor sometimes discussed involves isostatic rebound. After glaciers melted, land previously compressed by ice began rising slowly. That rebound continues in parts of the Great Lakes region today. However, the rates are measured in millimetres per year. Over thousands of years, this process can tilt shorelines slightly, altering relative water levels locally, but not draining entire basins. Sediment accumulation also affects lakes over geological time. Rivers carry sediments continuously, gradually filling basins. Eventually, given enough millions of years, a lake could fill enough to transition into wetlands, then land. For the Great Lakes, current sedimentation rates are far too slow for such an outcome within human timescales. This is a geological, not historical process. Hydrological balance remains the key stabilizing factor. Water enters through precipitation, and rivers roughly equal to what leaves through evaporation and outflow. That equilibrium fluctuates but persists. Without a significant structural breach lowering the outlet elevation, the lakes maintain their levels within natural ranges. Comparisons with other large lakes provide context. Some inland lakes have shrunk significantly due to climate change or water diversion. The Aral Sea in Central Asia is often cited. However, its shrinkage resulted largely from extensive river diversion for irrigation. The Great Lakes Basin does not currently face comparable diversion pressures, and protective policies reduce that likelihood. Understanding why the lakes are stable also helps clarify why the earlier thought experiment remains hypothetical. It allows exploration of hidden landscapes and environmental processes without implying imminent change. Scientific imagination often works this way, constructing scenarios to reveal underlying mechanisms. Public communication benefits from this clarity. Distinguishing between plausible environmental changes and purely theoretical exercises helps maintain informed discussion. Environmental stewardship depends on realistic assessment of risks rather than speculative extremes. Still, long-term geological history reminds us that landscapes do evolve. Millions of years from now, continental drift, erosion, and climate cycles could reshape North America substantially. Lakes may expand, shrink, or relocate. but those processes operate on timescales far beyond human planning horizons. In practical terms, the Great Lakes remain among the most stable freshwater systems on Earth. Monitoring programs track water levels, climate influence, ecosystem health, and geological stability continuously. Those observations support evidence-based management rather than speculation. This balance between stability and change offers perspective. The lakes are neither permanent nor fragile in the immediate sense. They exist within dynamic Earth systems, yet remain robust across centuries and likely millennia under current conditions. Reflecting on that stability often leads naturally to a broader consideration of how humans perceive permanence in landscapes. Features that seem timeless during individual lifetimes may still participate in slow, planetary cycles. Recognizing that duality encourages both appreciation of present landscapes and awareness of long-term environmental processes, a perspective that fits comfortably alongside the quiet continuity of water, time, and the evolving terrain surrounding it. If you have followed this journey from the first imagined drop in Shoreline to the fully exposed basin floors, you may notice something subtle. What began as a question about draining water gradually became a reflection on time itself. Not dramatic time measured in seconds or headlines, but layered time, geological time, ecological time, human time. All resting quietly beneath the surface of something most people see every day without thinking twice about it. The Great Lakes feel permanent when you stand beside them. The horizon stretches wide. Waves repeat their motion without visible beginning or end. Harbours operate year after year. Seasons cycle with familiar reliability. It is easy to assume that what looks stable today will look the same tomorrow. That assumption is part of how the human mind creates security. Stable landmarks help organise memory and expectation. Yet beneath that surface stability lies motion. Glaciers once advanced and retreated across this region. Ancient rivers carved valleys long before the lakes filled them. Forests grew, drowned, and left their traces. Ships crossed the water and sometimes sank. Industries rose along shorelines, leaving chemical signatures in sediment. Ecosystems formed intricate food webs dependent on temperature layers and nutrient cycles. Communities built identities around water that itself was shaped by forces far older than any city. Imagining the lakes drained was never about predicting loss. It was about revealing layers normally hidden. Remove the water in thought, and suddenly the quiet basin floor becomes readable. Geological scars show direction of ice flow. Buried forests reveal climate shifts. Shipwrecks freeze moments of human effort. Pollution layers record industrial growth and environmental learning. Even sound, something rarely mapped, shifts character when water disappears. The interesting realization is that none of those layers cease to exist simply because we do not see them. They are present now, beneath the surface, preserved by cold fresh water and sediment. The water acts as a curtain. We rarely question what lies behind it because daily life unfolds at the surface. Time operates similarly. We experience the present layer. Beneath it lie countless previous layers shaping what we see. The lakes are not just water, they are accumulated processes. Their depth holds physical history, but also evidence of adaptation and resilience. Consider how ecosystems adjust. As water recedes in the imagined scenario, fish migrate, wetlands shift, plants colonize new soil. Nothing responds with panic. Change unfolds step by step. Human systems mirror that pattern. Infrastructure adapts. Economies diversify. Cultural memory adjusts. Soundscapes evolve. Identity reframes itself. It becomes clear that permanence is often a matter of scale. Over a human lifetime, the Great Lakes appear steady. Over thousands of years, they fluctuate. Over millions, they are part of broader continental transformation. Recognizing that layered stability does not diminish their importance. If anything, it deepens appreciation. Water has always shaped human civilization. Rivers and lakes determine where cities rise. They influence trade routes, agriculture, recreation, and cultural imagination. Yet water itself is temporary in any one place over geological time. It flows, evaporates, freezes, returns. The basins remain longer than the water within them, and even they eventually change. When you picture the exposed lakebeds from this thought experiment, you might notice that what seemed empty at first quickly fills with meaning. Ridges and fault lines tell tectonic stories. Sediment layers record climate transitions. Artifacts reveal human persistence. Emerging plants signal ecological renewal. Silence where waves once sounded invites reflection rather than fear. There is also humility in this perspective. Human planning often focuses on decades. Geological processes stretch across millennia. Yet the two are connected. Decisions made over decades leave sediment layers that future observers could read. Industrial residues, conservation successes, infrastructure footprints all become part of the physical archive. The Great Lakes today function as reservoirs, climate moderators, ecological habitats, and cultural symbols. Their continued presence supports millions of people and countless species. Recognizing how much is layered beneath their surface encourages careful stewardship rather than complacency. At the same time, the exercise of imagining their absence sharpens perception of their presence. Standing at a shoreline feels different when you have mentally walked across the basin floor beneath it. You begin to sense depth, not only as vertical distance but as accumulated history. Time does not erase landscapes, it reshapes them. Water does not simply occupy space, it records what passes through it. Sediment does not merely settle, it stores information. The interaction among these elements produces the environments we inhabit and often overlook. If you think about where you're listening from right now, perhaps near water, perhaps far inland, you might notice the surfaces around you differently. What lies beneath them? What stories are layered quietly below your everyday horizon? Landscapes rarely announce their history. They wait. And so the Great Lakes remain, vast and reflective, holding their layered past beneath a surface that appears unchanged from one morning to the next. The question was never only about draining them. It was about understanding that even the most familiar places contain unseen depth, and that time, moving steadily whether we notice or not, shapes everything we assume will always stay the same.